Every second, the universe expands, unveiling profound mysteries that challenge the very fabric of our understanding. From the captivating intricacies of time and space to the bewildering behaviors of celestial bodies, the cosmos persistently tests everything we think we know. As we embark on this cosmic journey, we'll dive into the depths of space exploration, pondering the tantalizing possibility of life beyond Earth and unearthing the age-old enigmas that have perplexed humanity for millennia. Among the most compelling theories about the origin of the universe are the Big Bang Theory, the inflationary universe model, and various alternative cosmological hypotheses. The Big Bang Theory remains the most widely accepted explanation in the scientific community. It proposes that around 13.8 billion years ago, the universe began as an intensely hot and dense singularity. This singularity then expanded rapidly, giving birth to space, time, matter, and energy, the very building blocks of our observable universe. Following this monumental expansion, the inflationary universe model further refines our understanding, suggesting a dramatic burst of accelerated growth during the first fraction of a second after the Big Bang. This period of inflation smoothed out the early universe, laying the groundwork for the cosmic structures we observe today: galaxies, stars, and clusters of galaxies. This model also offers an explanation for certain cosmic phenomena, such as the uniformity of the cosmic microwave background radiation, the afterglow of the Big Bang itself. Yet, not all scientists accept these traditional explanations. The multiverse theory, for instance, introduces the possibility that our universe might not be unique, but rather one of countless others, each governed by its own distinct physical laws and constants. This raises intriguing philosophical and scientific questions about existence itself. What are the conditions necessary for life, and is it possible for them to exist elsewhere in the vast expanse of the multiverse? Such ideas encourage deep reflection, blurring the lines between science and philosophy. These theories about the origin of the universe lead us to profound questions about time, space, and existence, igniting both scientific investigation and philosophical inquiry. As we ponder these origins, scientists also consider various scenarios for the future of the universe, some of which present fascinating, if unsettling, possibilities. One of the most widely discussed future outcomes is the Big Freeze. This theory envisions an endlessly expanding universe, with galaxies drifting farther apart as the eons pass. Stars will burn out, leaving behind a cold, dark cosmos filled with black holes and the fading remnants of what once was. Observations of distant supernovae suggest that the universe's expansion is accelerating, lending credibility to the Big Freeze scenario. Another hypothesis is the Big Crunch, which suggests that if the universe's density reaches a certain threshold, gravitational forces will eventually slow the expansion, reversing the process and pulling everything back into a single dense point, reminiscent of the conditions that existed at the beginning of the universe. This theory finds some support in measurements of the cosmic microwave background radiation, which provide insight into the universe's expansion rate and overall density. A more recent and somewhat startling theory, the Big Rip, proposes that the expansion of the universe could accelerate to such an extent that it tears apart galaxies, stars, and even atoms themselves. This catastrophic event could be driven by dark energy, a mysterious force that is causing the observed acceleration of the universe's expansion. The effects of dark energy are still poorly understood, but current observations suggest it will play a pivotal role in determining the ultimate fate of the cosmos. Each of these theories is grounded in scientific evidence collected through astronomical observations and sophisticated cosmological models. As technology advances and more data becomes available, our understanding of the universe evolves, allowing scientists to refine their predictions about what the far future might hold for a universe that is constantly in motion. One of the key players in shaping the structure and behavior of the universe is dark matter. Comprising roughly 25% of the cosmos, dark matter is invisible and does not interact with electromagnetic forces, making it undetectable by traditional means. Instead, its presence is inferred through its gravitational effects on visible matter. The most direct evidence of dark matter's existence comes from its influence on galaxies. Dark matter exerts a powerful gravitational pull, forming a halo around galaxies that helps to hold them together. Without this unseen mass, galaxies would not have the necessary gravitational forces to prevent their stars and gas from flying apart as they rotate. Observations of galaxies reveal that their outer regions rotate faster than would be expected if only visible matter were present. This discrepancy provides strong evidence for the existence of dark matter, suggesting that there is far more mass in the universe than we can directly observe. As our understanding of the universe continues to deepen, we are left with more questions than answers. What lies beyond the observable horizon? How did life come to be on our planet, and does it exist elsewhere in the vast reaches of space? Will the universe continue to expand forever, or will it eventually collapse? These mysteries and many more continue to fuel our curiosity, pushing the boundaries of science and human knowledge into uncharted territory. Dark matter plays an essential and intriguing role in the cosmos, particularly in the formation of galaxies during the early stages of the universe. Just a few 100 million years after the Big Bang, minuscule fluctuations in the density of matter were amplified by dark matter's gravitational influence. This gravitational interaction caused matter to clump together, which allowed gas and dust to coalesce and form the very first galaxies. Far from being an invisible bystander, dark matter essentially served as the scaffolding around which galaxies took shape, deeply influencing their overall structure and distribution in the vast expanse of the universe. In the larger cosmic picture, galaxies are often found clustered together in vast groups. The unseen hand of dark matter plays a critical role in the formation and maintenance of these galaxy clusters. Acting like a cosmic glue, dark matter's gravitational pull holds galaxies together, fostering their interaction and coalescence. This not only helps in understanding the dynamics of individual galaxies, but also provides valuable insights into the large-scale structure of the universe itself. The cosmic dance of galaxies within these clusters tells a story, one intricately woven with the invisible threads of dark matter, offering a deeper understanding of how the universe has evolved over time. Alongside dark matter, another concept has emerged to fundamentally challenge our understanding of the universe: the theory of the multiverse. Traditional physics for centuries has been built on the assumption that we inhabit a single universe, where the laws of nature apply consistently across all of reality. However, the multiverse theory introduces a radical departure from this view. It suggests that numerous universes may exist, side by side, each governed by potentially different physical laws or constants. This idea upends our conventional understanding of reality, offering a vast interconnected framework of alternate realities that could be operating in parallel with our own. One of the most compelling arguments for the multiverse comes from quantum mechanics, particularly the many worlds interpretation. According to this theory, every decision or quantum event leads to the creation of a new universe. Essentially, every possible outcome of every decision, no matter how trivial, branches into its own separate reality. For example, in one universe, you might opt for coffee, while in another, you choose tea. This radical new perspective suggests that every possibility, no matter how improbable, exists somewhere in the multiverse. Cosmology also provides fertile ground for multiverse speculation. The theory of cosmic inflation, which explains the rapid expansion of the universe immediately after the Big Bang, suggests that this expansion could have led to the creation of isolated bubbles of space-time. Each of these bubbles may have evolved into its own universe, governed by its own unique set of physical laws. This idea encourages scientists to rethink foundational concepts like space-time and existence, broadening the scope of their inquiries to consider not just our observable universe, but a vast ensemble of realities that might lie beyond our reach. The implications of the multiverse theory stretch far beyond science alone. They resonate with deep philosophical questions about existence itself. If multiple universes are indeed real, it forces us to confront the nature of our own reality. Are we just one of countless variations? Does our universe hold a special place in the grand scheme of things, or is it merely one thread in an infinite tapestry of possibilities? The idea of an interconnected web of alternate realities challenges our understanding of existence, prompting us to expand our intellectual horizons and consider the infinite possibilities that might lie beyond the confines of what we know. Meanwhile, dark energy remains one of the most mysterious and perplexing components of our universe. Making up nearly 70% of the cosmos, dark energy is believed to play a significant role in the accelerated expansion of the universe. Despite its prevalence, its true nature and origin remain elusive, and various theories have been proposed to explain it. One of the leading ideas is the cosmological constant, which was first introduced by Albert Einstein in 1923. This theory suggests that dark energy is a constant energy density that fills space uniformly. Regardless of the universe's expansion, this energy remains constant, effectively acting as a kind of anti-gravity force that causes galaxies to drift apart. An alternative and equally intriguing concept is quintessence, a dynamic form of dark energy that can evolve over time. Unlike the cosmological constant, which remains fixed, quintessence proposes that dark energy consists of a scalar field that changes. As this field evolves, it could alter the rate of the universe's expansion over time. Quintessence offers a fascinating avenue for connecting dark energy with other fundamental forces and theories in physics, adding another layer of complexity to our understanding of the cosmos. Additionally, modified gravity theories provide alternative perspectives. Some scientists propose that our understanding of gravity, as formulated by Einstein's general theory of relativity, may need revision to account for the effects typically attributed to dark energy. One such theory, known as FR gravity, seeks to modify the equations of general relativity to explore how gravity behaves on cosmic scales. This could potentially unveil hidden aspects of dark energy, offering alternative explanations for the acceleration of the universe's expansion. String theory also offers another possibility. Dark energy might be linked to the existence of extra dimensions. If our universe contains more dimensions than we can perceive, dark energy might be the result of interactions between our three-dimensional universe and these additional dimensions. This theory suggests that dark energy is not simply a force acting in our visible universe, but might arise from a deeper, more complex framework of reality that we are only beginning to understand. Despite the variety of theories, it's clear that dark energy remains one of the most enigmatic components of the cosmos, and much remains to be uncovered about its true nature. Each of these hypotheses offers a unique perspective, showcasing the depths of mystery still present in the universe and the fascinating challenges that await scientists in their quest to unravel the truth. Finally, quantum mechanics continues to revolutionize our understanding of reality, acting as the key to unlocking some of the universe's deepest mysteries. By studying the behavior of particles at the quantum level, scientists are gaining insights into the fundamental nature of reality itself. Quantum principles like superposition and entanglement challenge traditional notions of space and time, revealing a universe that is far more interconnected and strange than we had ever imagined. These phenomena suggest that the universe operates in ways that defy classical logic, presenting an exciting frontier in our search for answers about the nature of existence. One of the most fascinating frontiers in science today is the potential for quantum mechanics to unlock profound mysteries, particularly in the realm of black hole physics. For decades, scientists believed that anything that fell into a black hole, be it matter or energy, was lost to the universe forever. But recent theoretical advancements in quantum mechanics suggest this may not be the case. It turns out that information, even the information about the contents of black holes, might not be entirely erased as was once assumed. This idea is rooted in one of the most mind-bending concepts in modern physics, the holographic principle. At its core, the holographic principle suggests that the entirety of a volume of space, every bit of information it contains, could be encoded on a two-dimensional surface that bounds it. If true, this concept has profound implications for our understanding of black holes. It means that everything that falls into them might be preserved in a form we don't yet fully understand. If scientists can fully grasp this, they may be able to unravel what happens inside black holes and perhaps redefine our understanding of space-time itself, offering tantalizing glimpses into how the universe is structured at its most fundamental levels. Beyond black holes, quantum mechanics could also hold the key to unlocking one of the most elusive goals in physics, a unified theory that merges quantum mechanics with Einstein's theory of general relativity. For years, these two pillars of modern physics have resisted integration. Quantum mechanics describes the behavior of subatomic particles, while general relativity explains the workings of large-scale objects like stars and galaxies. Yet, they don't comfortably fit together. However, new theoretical advancements, such as the study of quantum gravity, aim to reconcile these disparate descriptions of reality. A successful theory could bring clarity to some of the most puzzling phenomena in the universe, such as dark matter and dark energy, two mysterious forces that, together, make up 95% of the universe, yet remain poorly understood. The development of quantum technologies, such as quantum computing, has already begun to show how these discoveries can have practical implications. By simulating quantum systems with unprecedented accuracy, researchers are gaining the ability to model complex interactions in the universe more precisely than ever before. Each new revelation in quantum mechanics not only transforms our perspective on the cosmos, but also opens up new paths for exploration, paths that we may not have even imagined yet. Among the most powerful tools astrophysicists have in their quest to understand the universe is the cosmic microwave background radiation. This faint afterglow of the Big Bang holds clues to the universe's earliest moments, offering a snapshot of the universe when it was just 380,000 years old. At this point, the cosmos had cooled enough for protons and electrons to combine into neutral hydrogen atoms, allowing light, previously trapped in a hot, dense soup of particles, to travel freely through space. The light from this era, now stretched into microwave wavelengths, continues to permeate the cosmos, providing scientists with a wealth of information about the early conditions of the universe. By studying this radiation, scientists can learn about the universe's temperature and density in its infancy. Tiny fluctuations in temperature across the cosmic microwave background map offer a record of how matter was distributed in the early universe. These fluctuations are believed to be the seeds from which galaxies and other large-scale structures formed as the universe expanded and cooled over billions of years. This subtle map of the early cosmos allows astrophysicists to reconstruct the timeline of cosmic evolution from the birth of the universe to the formation of the galaxies we observe today. Furthermore, the cosmic microwave background has revealed crucial details about the processes that shaped the universe. Its uniformity across the sky is one of the key pieces of evidence supporting the theory of cosmic inflation. This theory suggests that the universe underwent an extraordinarily rapid expansion immediately after the Big Bang, smoothing out any irregularities and explaining why distant regions of the universe have such similar temperatures, even though they are now far apart. This rapid expansion, stretching space itself, provided the necessary conditions for the universe to evolve into its current structure. By analyzing the cosmic microwave background, scientists can also estimate fundamental cosmological parameters, such as the age of the universe and its composition. This radiation has been stretched or redshifted by the expansion of the universe, allowing researchers to determine the proportions of ordinary matter, and dark energy, three components that make up the vast majority of the cosmos. This data not only enhances our understanding of the universe's past, but also provides a foundation for predictions about its future. One of the most profound consequences of the universe's expansion is its effect on our understanding of time. For centuries, time was considered a constant, flowing uniformly throughout the cosmos. Yet, the expansion of the universe challenges this view. As galaxies move away from one another, an observation confirmed by the redshift of their light, space itself stretches, which means that the very fabric of time may also be altered. In some parts of the universe, time may flow differently from other regions, especially when influenced by powerful gravitational fields, a phenomenon predicted by Einstein's theory of general relativity. This raises important questions about the nature of time itself, particularly when viewed across vast cosmic distances. For instance, the concept of the cosmic horizon, beyond which we cannot receive any information due to the rapid movement of galaxies, illustrates how our perception of time is intricately tied to the expansion of the universe. This horizon represents the limit of our observable universe, a boundary beyond which galaxies are receding faster than the speed of light. This cosmic barrier not only alters our understanding of space, but challenges our very concept of time itself, suggesting that what we perceive as time might be fundamentally different depending on our location in the cosmos. In sum, the universe is a vast, dynamic system in which time, space, and matter are constantly interacting in ways that challenge our deepest assumptions. Quantum mechanics and the exploration of cosmic phenomena offer new lenses through which we can view this mysterious cosmos, expanding our understanding and offering new pathways for future discovery. The discovery of dark energy has brought a new and profound layer of complexity to our understanding of the universe. Dark energy is the mysterious force believed to be responsible for the accelerated expansion of space. As this expansion continues to hasten, it presents a set of questions that challenge not only our understanding of the universe's structure, but also its ultimate fate. If the expansion keeps accelerating at this rate, it could have a monumental impact on future cosmological models. Some speculate that this relentless growth might even alter our conception of time itself. What if, in the distant future, galaxies drift so far apart that they no longer interact with one another? Imagine a scenario where the universe stretches out so vast and empty that all galaxies become invisible to each other. Such scenarios don't just have implications for how we understand the cosmos today. They force us to rethink the very nature of existence. For future civilizations, these changes could mean a profound shift in how history is understood, if it is even conceivable to think of history in such a fragmented, isolated universe. The idea of a universe continuing to expand indefinitely raises questions about whether anything or anyone will be around to witness its far-off future. Moreover, the expansion of the universe is not merely about the increasing distance between galaxies. It challenges the very concepts of time and space. As the universe continues to stretch, it invites us to reconsider how these concepts might evolve. Could time as we experience it become a fleeting, irretrievable phenomenon? Could the fabric of reality itself undergo changes that render our current models of time and space obsolete? The shape of the universe plays a key role in how we understand the laws of physics throughout space and time. Cosmologists have identified three primary geometries the universe might adopt: flat, open, and closed. Each of these shapes not only the structure of the universe, but also how the fundamental forces interact with matter and energy. In a flat universe, which aligns closely with current observations, the geometry allows the laws of physics to operate in predictable ways. Light travels in straight lines, and parallel lines never meet. This kind of universe suggests a perfectly balanced energy density, where expansion continues at a steady rate. The physical laws that govern this universe, such as those relating to gravity and electromagnetism, remain consistent and reliable, allowing us to understand the behavior of matter over vast distances. On the other hand, an open universe, which is one that curves outward, behaves quite differently. In such a universe, the density of matter is lower, and this causes a continuous, unbounded expansion. While light still travels straight over immense distances, its paths begin to diverge, making galaxies appear increasingly isolated. As a result, the universe would exhibit a cosmic horizon, a boundary beyond which nothing can be observed, no matter how advanced our instruments become. Here, the laws of physics still apply, but their influence on cosmic structures changes due to the expansive geometry. In a closed universe, the shape is akin to a sphere. Over time, the effects of gravity would eventually overcome the initial expansion, causing the universe to collapse back in on itself in a scenario known as the Big Crunch. As the universe contracts, gravitational forces would become increasingly powerful, altering the behavior of galaxies and stars, possibly even pulling them into one another. In this scenario, the laws of physics would still hold, but their effects would be far more pronounced due to the intense curvature of space-time. These three possible shapes, flat, open, and closed, are not mere theoretical constructs. They determine the long-term fate of the universe. Understanding them is essential for predicting how the universe might evolve and how the fundamental forces that govern the cosmos interact with the matter within it. Rogue planets add yet another layer of intrigue to our cosmic understanding. These wandering worlds drift through the galaxy unbound by the gravitational embrace of any star system. Unlike the familiar planets in our solar system, which orbit the sun, rogue planets have been ejected from their original star systems, either through violent interactions with other celestial bodies or due to gravitational encounters. This lack of attachment to a star means rogue planets lack the stable energy sources, such as sunlight, that drive the climates and atmospheres of planets within star systems. The absence of a stable energy source makes rogue planets intriguing. Some may be freezing cold and shrouded in mystery, while others might retain the heat from their formation, creating environments unlike any we can find in the known universe. What's more, some rogue planets are thought to harbor subsurface oceans, which raises the tantalizing possibility that life could exist in isolation, far from the warmth of any star. The existence of rogue planets challenges traditional definitions of planets themselves. They don't fit neatly into the categories we have established because they don't orbit a star. Their existence calls into question the very nature of what it means to be a planet. Furthermore, estimates suggest that rogue planets may outnumber stars in our galaxy. This staggering possibility hints at an astonishing variety of worlds, each unique in its formation and conditions. As our observational technologies improve, the study of rogue planets could open up new avenues of exploration. It may provide us with insights into planetary formation, migration, and even the potential for life beyond traditional star systems. Exoplanets, or planets orbiting stars outside our solar system, are another frontier in our search for life beyond Earth. Thousands of these distant worlds have been confirmed, and they offer a vast diversity of environments. Through missions like the Kepler Space Telescope and the Transiting Exoplanet Survey satellite, astronomers have identified planets in the so-called habitable zone, where conditions might allow for the presence of liquid water, an essential ingredient for life as we know it. The study of exoplanets brings us one step closer to understanding the potential for life elsewhere in the universe. By analyzing their atmospheres, scientists can look for chemical signatures that may suggest biological activity. For example, the simultaneous presence of oxygen and methane, gases that tend to react with each other and break down unless replenished, could be an indicator of life. The discovery of such a combination would be groundbreaking, suggesting that these distant worlds may host complex, self-sustaining ecosystems. The exploration of rogue planets, exoplanets, and dark energy reveals how much there is still to learn about the universe's past, present, and future. These discoveries not only expand our understanding of cosmic phenomena, but also invite us to ponder the fate of life, time, and existence itself in a universe that is ever-changing and constantly evolving. The discovery of exoplanets has drastically altered our previous assumptions about where life might thrive. As we delve deeper into this vast frontier, it becomes evident that the variety of exoplanets is more complex and diverse than we ever imagined. Some exoplanets are tidally locked, meaning that one side perpetually faces their star, creating extreme temperature differences between the scorching day side and the freezing night side. Other planets feature unique atmospheric compositions or climates that are extreme by Earth standards, environments that challenge our conventional understanding of habitability. These findings push scientists to reconditions under which life could exist. Rather than sticking to traditional models, they are exploring the possibility of life forms that could adapt to these unfamiliar extreme conditions. This fundamentally shifts our perspective on what life can be, broadening the scope of what constitutes a habitable world. As the field of exoplanet research advances, particularly with the exciting missions planned for the future, the potential to uncover new worlds and possibly even new forms of life is growing. The search for biosignatures, indicators of life, fuels scientific curiosity and offers a glimmer of hope that we might not be alone in the universe. It encourages a deeper exploration of our place in the cosmos, making us rethink what we know about life and its possibilities. In the realm of extreme celestial objects, neutron stars stand as some of the densest entities known to science. These compact remnants of massive stars pack a mass greater than that of the Sun into a sphere only about 12 kilometers in radius. To give some perspective, a sugar cube-sized amount of neutron star material would weigh as much as an entire mountain on Earth. This extraordinary density results from the immense gravitational forces that occur when a massive star collapses after a supernova explosion. What makes neutron stars particularly fascinating is their composition. They are primarily made up of neutrons, subatomic particles that carry no electrical charge. When a massive star exhausts its nuclear fuel, its core collapses under the force of gravity, causing protons and electrons to merge and form neutrons. This process creates the neutron star, which can spin incredibly fast, some rotating hundreds of times per second. These rapid rotations generate beams of electromagnetic radiation, which we observe as pulsars. Neutron stars also possess an intense gravitational field, which is about 2 billion times stronger than Earth's. This gravity doesn't just affect the immediate vicinity, it warps the very fabric of space-time around them. This warping creates fascinating optical effects known as gravitational lensing, where the light from distant stars and galaxies is bent around the neutron star. This phenomenon makes neutron stars invaluable for studying the nature of gravity itself. The surface of a neutron star is incredibly hot, with temperatures that can reach millions of degrees. This extreme heat results in the emission of X-rays, which astronomers can detect and study. By observing these X-rays, scientists gain insight into the star's composition, magnetic field, and internal structure. Each of these characteristics makes neutron stars captivating subjects of cosmic research, providing us with new windows into the fundamental workings of the universe. Black holes, on the other hand, present one of the greatest enigmas in our understanding of gravity and space-time. According to Einstein's theory of general relativity, massive objects distort the fabric of space-time, and this curvature is what we experience as gravity. But when a star reaches the end of its life and collapses under its own gravity, it can compress matter into an infinitely dense point, creating what is known as a singularity. This singularity lies at the core of a black hole, surrounded by an event horizon, a boundary beyond which nothing, not even light, can escape. What is particularly intriguing about black holes is how they challenge the very foundation of general relativity. At the singularity, the equations that describe gravity break down, creating a paradox where the known laws of physics no longer apply. This creates a profound conflict between general relativity, which explains gravity at large scales, and quantum mechanics, which governs the behavior of particles at the smallest scales. This discrepancy suggests that there may be new, unseen physics at play in the regions dominated by black holes, potentially offering clues to a deeper understanding of the universe. Scientists are still grappling with how to reconcile these two frameworks, as the study of black holes could reveal new insights into the fundamental forces of nature. As we continue to explore these cosmic phenomena, it becomes clear that the universe is far more complex and mysterious than we ever imagined. With each new discovery, we edge closer to unlocking the secrets of the cosmos and our place within it. Moreover, black holes pose a profound challenge to our understanding of the universe, particularly when it comes to the nature of information. At the heart of the information paradox lies a fundamental question: what happens to the information contained in matter that falls into a black hole? According to quantum theory, information cannot be destroyed, but black holes seem to defy this principle. This has sparked significant debates among physicists and cosmologists, as the fate of this information remains one of the most puzzling mysteries in modern science. Some theories propose that the information might not be lost at all. Instead, it could be preserved in some form, possibly being released into the universe through black hole radiation, a phenomenon famously predicted by physicist Stephen Hawking. This radiation, known as Hawking radiation, suggests that black holes might not be entirely black after all, and their interactions with the quantum realm could provide critical insights into the nature of space, time, and matter. These discussions continue to fuel ongoing research, inspiring new theories that may one day lead to a more unified understanding of the cosmos. The very existence of black holes forces us to reconsider the way we perceive time and reality. Near a black hole, time behaves very differently. Time itself flows more slowly in the intense gravitational field near a black hole, relative to an observer far away from it. This phenomenon, known as time dilation, provides a stunning glimpse into the impact gravity can have on the fabric of time. It illustrates the strange and intricate relationship between matter, energy, and time, revealing just how much more we need to understand about the fundamental dynamics of the universe. Yet black holes do not simply challenge our existing theories, they ignite curiosity and exploration, encouraging scientists to dig deeper into the very workings of nature. Supermassive black holes, in particular, represent some of the most enigmatic objects in the cosmos, their mysteries lying at the very heart of the most massive galaxies, including our own Milky Way. These cosmic giants hold secrets that challenge our comprehension of cosmic evolution. Despite their ubiquity in the universe, the processes that lead to their formation and growth remain shrouded in uncertainty. One prevailing theory suggests that supermassive black holes could have formed through the rapid collapse of massive stars in the early universe. Alternatively, they might have emerged from the gradual merging of smaller black holes over time. However, the precise mechanisms that govern their creation remain subjects of intense debate among astrophysicists. The formation of these colossal objects raises fundamental questions about the nature of the early universe and the processes that allow such massive structures to emerge so quickly. Perhaps one of the most fascinating aspects of supermassive black holes is their deep and complex relationship with the galaxies that host them. Observations reveal that as these black holes consume material from their surroundings, they can release vast amounts of energy in the form of powerful jets and radiation. This process, known as accretion, profoundly affects the evolution of the host galaxy. The energy emitted during accretion can influence star formation and drive the dynamic changes occurring in the galactic environment. However, the exact mechanisms behind this interaction, the cause and effect between black holes and galaxies, remain an area of active research. Over the course of their lifetimes, supermassive black holes can also shed light on the growth of the universe itself. For instance, when the universe was only about 1 billion years old, several of these giant black holes had already formed, suggesting they can gain mass at a truly staggering rate. Understanding how they grew so quickly challenges our existing theories of cosmic evolution, forcing us to rethink the conditions in the early universe that allowed such rapid accumulation of mass. Furthermore, the potential existence of intermediate mass black holes, those with a mass between stellar and supermassive black holes, adds yet another layer of complexity to our understanding of black hole growth. These black holes could help explain the process through which supermassive black holes form and evolve, offering a missing piece of the puzzle. As scientists continue to gather data through advanced telescopes and observational missions, there is hope that we will one day uncover the deep mysteries of these enigmatic objects, further enriching our understanding of the cosmos itself. Quasars, or quasi-stellar objects, serve as brilliant beacons that illuminate the distant reaches of the early universe. Powered by supermassive black holes at the centers of galaxies, these incredibly luminous objects are formed when black holes actively consume surrounding gas and dust. As this matter spirals inward toward the event horizon, it heats up, emitting vast amounts of energy in the form of intense radiation. Quasars are among the brightest phenomena in the cosmos, outshining their entire host galaxies by many orders of magnitude. When astronomers observe quasars, they are, in effect, looking back in time. The light emitted by these objects has traveled for billions of years to reach us, meaning that studying them is like peering into the distant past. The spectrum of light from quasars holds critical information about the conditions in the early universe, offering a snapshot of the cosmos as it existed billions of years ago. By analyzing the light from quasars, scientists can gather insights into the composition of the universe at the time when these galaxies were formed. For example, the presence of specific elements in quasar spectra can reveal how much of the universe's ordinary matter was converted into stars, and how those stars contributed to the chemical enrichment of their surrounding environments. This information provides important clues about how galaxies formed and evolved, helping scientists reconstruct the timeline of cosmic history. The vast distances to these quasars allow researchers to estimate when the galaxies that host them were formed, helping to refine our understanding of the universe's age and its growth. Moreover, quasars provide a unique opportunity to explore the distribution of matter across the universe. As quasars are often found in regions where matter is highly concentrated, their distribution patterns offer crucial information about the underlying gravitational influences of dark matter. By studying how quasars are distributed throughout the sky, astronomers can better understand the role of dark matter in shaping galaxies and large-scale cosmic structures. These observations help reveal the forces that have shaped the universe from the hot, dense state following the Big Bang to the intricate web of galaxies and clusters that we observe today. The study of quasars not only sheds light on the individual galaxies that host them, but also provides invaluable insights into the broader evolution of the universe. Their ability to transcend both time and space makes them indispensable tools in unraveling the mysteries of early galaxy formation. Each quasar serves as a piece of the cosmic puzzle, helping scientists to piece together the complex processes that have shaped the universe as we know it. By examining these luminous beacons, we can better understand the vast and intricate tapestry of cosmic history, revealing the profound forces that have governed the evolution of the universe over billions of years. In the vast expanse of our solar system, several moons stand out not only for their extraordinary characteristics, but also for the mysteries they harbor beneath their icy, gaseous, or volcanic surfaces. These moons, each distinct in its composition and environment, offer a glimpse into the broader processes that shaped our cosmic neighborhood and may even hold clues to the existence of life beyond Earth. Europa, one of Jupiter's most captivating moons, is an object of intense scientific scrutiny. Its surface, an expanse of smooth, gleaming ice, hides something far more intriguing beneath, an ocean of liquid water. This subsurface ocean, protected by the ice shell, is believed to be kept liquid by the moon's internal heat, possibly generated by tidal forces from Jupiter's immense gravitational pull. The potential for liquid water is one of the most compelling reasons Europa is central to the search for extraterrestrial life. Scientists believe that within this dark, hidden ocean, conditions might exist that are conducive to life, offering a tantalizing possibility that microorganisms, or even more complex life forms, could thrive in this frozen world. Further from Jupiter, Titan, Saturn's largest moon, presents an entirely different kind of enigma. Titan is enveloped in a thick, nitrogen-rich atmosphere, so dense that it shrouds the moon's surface in a perpetual haze. The surface itself is an alien landscape, rivers, lakes, and seas composed not of water, but of liquid methane and ethane. Titan's frigid environment, with temperatures hovering around minus 290 degrees Fahrenheit, makes it inhospitable by earthly standards. However, the moon's exotic chemistry sparks speculation about the possibility of life forms that could survive in such an extreme, methane-dominated environment. Titan's atmosphere and liquid hydrocarbon lakes offer scientists a unique opportunity to study processes that could parallel the early stages of life on Earth, where conditions might have been similarly harsh but capable of supporting the first steps of biological evolution. Meanwhile, Io, another of Jupiter's moons, takes a radically different approach to the idea of alien worlds. It is, in fact, the most volcanically active body in the entire solar system. The surface of Io is a chaotic mosaic of erupting volcanoes, rivers of molten lava, and massive volcanic plumes that shoot sulfurous gases hundreds of miles into space. This intense geological activity is largely due to the gravitational interactions between Io, Jupiter, and the other Galilean moons. These tidal forces create immense friction within Io's interior, generating the heat that fuels its volcanic eruptions. The ever-changing landscape of Io represents an environment in constant flux, reshaped and sculpted by forces deep within the moon. Its fiery surface stands in stark contrast to the icy moons of Jupiter, offering a reminder of the diverse ways celestial bodies can evolve and transform. Then there is Triton, Neptune's largest moon, which has a distinct and peculiar orbit that sets it apart from the other moons in our solar system. Unlike most moons that orbit their planets in the same direction as the planet's rotation, Triton follows a retrograde orbit, moving in the opposite direction. This unusual orbital path suggests that Triton may not have originally formed in Neptune's vicinity, but was captured by the planet's gravity, possibly originating from the distant Kuiper belt. Its icy surface is punctuated by geysers that erupt nitrogen gas into the thin atmosphere, a phenomenon that suggests Triton is geologically active. The combination of Triton's backward orbit and its active geology hints at a history shaped by processes far different from the other moons, adding a layer of mystery to its origins and role in the solar system. Each of these moons challenges our understanding of the cosmos and continues to ignite our curiosity about the potential for life beyond Earth. But the wonders of our solar system are not confined to the moons alone. The asteroid belt, a vast region stretching between the orbits of Mars and Jupiter, offers a wealth of information about the solar system's early days. The asteroid belt is not merely a collection of rocky debris, but rather a time capsule filled with remnants of the primordial materials that existed during the formation of the solar system, approximately 4.6 billion years ago. Unlike the planets, which have undergone extensive geological transformation, many asteroids have remained largely unchanged. These ancient bodies preserve a record of the chemical and physical conditions that existed in the solar system's youth. By studying asteroids, scientists can gain valuable insights into the building blocks of planets, including materials like rock, metal, and organic compounds that were prevalent in the early solar system. These compounds may hold the secrets to the formation of Earth and the other planets, shedding light on the complex processes that led to the creation of our own world and its neighboring planets. Asteroids also provide a unique opportunity to understand the dynamics of the solar system itself. The gravitational influence of Jupiter has had a profound effect on the asteroid belt. Jupiter's immense mass exerts such a strong gravitational pull that it prevents the material in the belt from coalescing into a planet. Instead, the belt remains in a delicate balance, with asteroids orbiting the Sun while interacting with one another in a gravitational dance. Studying the variations in asteroid orbits and their interactions with other celestial bodies helps scientists piece together the early gravitational dynamics that influence the evolution of the solar system. Missions to these asteroids, such as the ones conducted by spacecraft like NASA's OSIRIS-REx, have allowed for the collection of samples that further illuminate the chemical composition and isotopic ratios of these ancient objects, offering a direct window into the materials that formed our solar system. As we continue to explore and study the asteroids, moons, and other celestial bodies within our solar system, we not only unravel the history of our own planet, but also gain a deeper understanding of the processes that drive planetary evolution across the cosmos. The search for life and the understanding of our solar system's formation are intimately tied, and with each new discovery, we inch closer to answering questions that have puzzled humanity for centuries. In addition to these moons and asteroids, the exploration of Mars has revealed some astonishing possibilities about the planet's past and its potential for supporting life. Recent studies, particularly from the Mars Reconnaissance Orbiter and the Perseverance rover, have unveiled evidence suggesting that liquid water may exist beneath the Martian surface. Spectroscopic data points to the presence of salty, briny water that could remain liquid even in the extreme cold of Mars, where temperatures often plunge well below freezing. This finding has profound implications, as liquid water is considered a fundamental prerequisite for life as we know it. Mars's surface features also hint at a much wetter past. The discovery of ancient riverbeds, lakebeds, and valleys carved by flowing water paints a picture of a planet that was once far more hospitable than it is today. This evidence suggests that Mars may have once had a climate that supported liquid water on its surface, and that water could have played a key role in shaping the planet's geology. Additionally, scientists have detected hydrated minerals, substances that formed in the presence of water, further supporting the idea that water has had a significant influence on the Martian landscape over time. As missions to Mars continue to probe its surface and subsurface, they reveal the true extent of the planet's history with water. While Mars is far from Earth in its current state, the tantalizing possibility that life may have once existed, or could still exist in some dormant form, keeps scientists eager to explore every corner of the red planet. From its frozen poles to its ancient riverbeds, Mars holds secrets that could change our understanding of life in the universe. Moreover, researchers have uncovered compelling evidence of seasonal dark streaks that run down the slopes of Mars, known as recurring slope lineae. These mysterious features appear to ebb and flow with the changing Martian seasons, suggesting the presence of transient liquid water. While the exact nature of these streaks remains under investigation, their seasonal appearance hints at a dynamic process still unfolding on the red planet, and they have sparked intense interest among scientists. The prospect that liquid water might still exist on Mars, even in brief, transient forms, raises profound questions about the planet's geological activity and the possibility of life. Could microbial life hiding in Martian aquifers beneath the surface still survive in these water-rich environments? This tantalizing question adds urgency to the ongoing search for life beyond Earth, particularly in the context of Mars's history, which may have once supported more stable, liquid water conditions. The accumulation of evidence pointing to the potential for liquid water on Mars has propelled space exploration to new heights, with both scientists and explorers eager to understand whether life could still exist in the Martian depths, awaiting discovery. In a different realm of cosmic phenomena, fast radio bursts stand out as some of the most perplexing and enigmatic occurrences ever observed. Captured by radio telescopes on Earth, these bursts of radio waves last only a fraction of a second, but release an astonishing amount of energy, equivalent to the combined output of hundreds of millions of suns. Discovered in 2007, fast radio bursts have sparked a variety of theories regarding their origins. One of the most widely discussed hypotheses is that these bursts are produced by magnetars, highly magnetized neutron stars capable of emitting bursts of energy through their intense magnetic fields. Other theories suggest that the bursts may arise from the merger of two neutron stars, which generates not only powerful radio waves, but also gravitational waves, ripples in the fabric of space-time. The possibility that fast radio bursts could be the result of supernova explosions, or even the extreme phenomena surrounding black holes, has also been considered. Some have even proposed that these bursts could be signals from advanced extraterrestrial civilizations, although this remains speculative and is far from the mainstream view. The significance of fast radio bursts goes beyond their fleeting duration. They offer a unique window into understanding cosmic phenomena that were previously beyond our grasp. By studying the way these bursts interact with the interstellar medium, the matter and energy that exists between galaxies, scientists can gain valuable insights into the density and composition of the space through which they travel. As these bursts pass through the interstellar medium, they leave behind subtle clues that help researchers reconstruct the broader conditions of the universe. Every discovery in this area raises new questions and deepens our curiosity about the vast cosmos, highlighting the ongoing transformation of modern astrophysics. Similarly, gravitational waves, ripples in space-time, first predicted by Albert Einstein over a century ago, have revolutionized our understanding of the universe. These waves are created when massive objects, such as black holes or neutron stars, collide or merge, generating disturbances that ripple across space at the speed of light. The first direct detection of gravitational waves occurred in 2015 when scientists observed waves originating from the collision of two black holes. This momentous discovery not only confirmed Einstein's theory of general relativity, but also opened an entirely new frontier in astronomy. Thanks to gravitational waves, scientists are now able to observe phenomena that were once invisible, offering unprecedented insights into the most extreme events in the universe. For example, the merging of neutron stars, events that produce both gravitational and electromagnetic waves, provides crucial information about the origins of heavy elements like gold and platinum. This discovery challenges previous assumptions about the formation of such elements, offering new theories on how they are created in the depths of space. Gravitational wave detection has also allowed researchers to study black hole mergers in much greater detail, offering information about their masses, spins, and other characteristics. These findings have reshaped our understanding of black hole populations, suggesting that there may be many more black holes lurking in the cosmos than previously thought. The ability to detect gravitational waves has had a profound impact on our understanding of stellar evolution. These waves have provided new insights into how stars die, how black holes form, and how they interact with one another. As we continue to explore these waves, they hold the potential to unlock even more of the universe's deepest secrets, offering clues about the nature of space, time, and the cosmos itself. The future of astrophysical research may very well be shaped by the ongoing study of gravitational waves, as they continue to challenge our most fundamental assumptions about the universe. In recent years, advancements in observational technology have propelled us into a new era of exploration, one that invites collaboration across diverse scientific disciplines. Physicists, astronomers, and engineers now work in tandem, breaking down the barriers between their fields and pushing the boundaries of what we know. This collaborative spirit not only enhances our technological capabilities, but also expands our understanding of the universe at a fundamental level. As our ability to detect gravitational waves improves, we are presented with an unprecedented opportunity to study some of the most violent and energetic processes in the cosmos. The more we detect, the deeper our insight into the mechanics behind galactic evolution becomes, shedding light on the forces shaping the universe's most extreme events. Among the most remarkable phenomena we are beginning to understand are gamma ray bursts, immense fleeting explosions that are among the most powerful events in the universe. These bursts, lasting anywhere from mere milliseconds to several minutes, emit an amount of energy far greater than the total energy output of our sun over its entire lifetime. Gamma ray bursts, or GRBs, are the most intense form of electromagnetic radiation known to science. Their study offers astronomers valuable clues into the extreme environments that give rise to these events, providing insight into some of the most energetic processes taking place across vast expanses of space. The origins of gamma ray bursts are closely linked to two catastrophic cosmic events: the collapse of massive stars and the merger of neutron stars. When a massive star runs out of fuel, it undergoes a violent implosion, ultimately forming a black hole. During this process, the star releases a concentrated beam of gamma rays, often referred to as a gamma ray jet, that can travel millions of light years, carrying energy across the universe. Observing these bursts of energy, astronomers can study the environmental conditions that lead to such powerful outcomes. Furthermore, they gain insights into the life cycles of stars and the evolution of galaxies, revealing how stars end their existence and what happens in their wake. But gamma ray bursts don't only tell us about stellar death, they also serve as cosmic beacons, enabling scientists to probe parts of the universe that are otherwise out of reach. The extreme luminosity of these events allows them to be observed from vast distances, making them invaluable tools for studying the early universe. They give us a snapshot of the conditions that existed billions of years ago, offering clues about the rates of star formation, the expansion of the universe, and the fundamental nature of gravity under extreme conditions. The afterglows of these bursts, fainter emissions that follow the initial explosion, can provide additional information about the environments surrounding black holes and neutron stars, further expanding our understanding of the cosmos. Just as gamma ray bursts illuminate the universe's most energetic phenomena, supernova, particularly a type known as Type 1a supernova, play a crucial role in helping astronomers chart the history of the universe itself. These stellar explosions occur in binary star systems, where one of the stars is a white dwarf. The white dwarf accumulates material from its companion star, and once it reaches a critical mass, it detonates in a spectacular explosion. What makes Type 1a supernovae so valuable is their remarkable consistency in peak brightness. This predictable behavior allows scientists to use them as standard candles, reliable markers for measuring astronomical distances with great accuracy. By observing the light emitted during these supernovae events, astronomers can calculate how far away these objects are, offering vital information about the scale of the universe. When combined with redshift data, shifts in the light's wavelength caused by the expansion of space, these measurements allow scientists to track the rate at which the universe is expanding. By analyzing these observations, researchers can create a timeline of cosmic expansion and backtrack to estimate the universe's age. This process has led to a refined understanding, with estimates now suggesting the universe is approximately 13.8 billion years old. Furthermore, the study of supernovae has provided key insights into dark energy, the mysterious force believed to be driving the accelerated expansion of the universe. The discovery that the universe's expansion is not slowing down, but rather speeding up, was made possible through observations of distant supernovae. This revelation has profound implications, not only for the history of the universe, but also for its ultimate fate. As scientists continue to explore this cosmic acceleration, they are faced with questions that challenge our understanding of the very fabric of reality. Another concept that is increasingly captivating the imagination of scientists is the idea of cosmic strings. These hypothetical structures, if ever discovered, could significantly alter our understanding of the universe's structure. Cosmic strings are thought to have formed in the early moments of the universe during a phase transition, existing as one-dimensional defects in space-time. Incredibly thin, yet incredibly dense, they are believed to stretch across vast distances in space, potentially influencing the gravitational field in ways that have yet to be fully understood. The discovery of cosmic strings would have profound implications for the field of theoretical physics. These objects are thought to interact with gravity in unique ways, bending light and possibly distorting the distribution of galaxies and galaxy clusters. By studying these potential cosmic features, scientists would gain new insights into dark matter and the forces that govern the universe's large-scale structure. More importantly, cosmic strings could help bridge the gap between different areas of physics, from quantum mechanics to general relativity. In particular, their study could reveal new connections between string theory and the general theory of relativity, bringing us closer to a unified theory of the fundamental forces and particles that govern the cosmos. In the pursuit of knowledge, the discovery of such phenomena could be the key to unraveling the deepest mysteries of the universe. From the violent bursts of gamma rays to the faint glow of supernovae and the theoretical fabric of cosmic strings, each discovery pushes us further into the unknown. It is this relentless curiosity and the ever-expanding scope of scientific inquiry that continue to propel our understanding of the universe, urging us to ask ever bolder questions about the nature of existence and the forces that shape our reality. Cosmic strings, theoretical structures that stretch across the universe, hold the potential to challenge and expand our understanding of the cosmos. These mysterious phenomena could influence the rate at which the universe is expanding, prompting revisions to our calculations of both the universe's age and its eventual fate. As we study these potential relics from the early universe, they could uncover new mysteries about the origin and evolution of everything we know, pushing both theoretical and observational astronomy in ways we have yet to fully comprehend. The discovery of cosmic strings might not just refine existing models, but radically alter the framework through which we view the universe's evolution, providing a new lens through which to explore the cosmos. Meanwhile, cosmic rays, high-energy particles that travel vast distances through space, play a critical role in our understanding of astrophysics. These particles, which mostly consist of protons and atomic nuclei, originate from extreme and energetic sources such as supernovae, active galactic nuclei, and even our sun. As cosmic rays collide with atoms in Earth's atmosphere, they produce a cascade of secondary particles that offer astronomers an invaluable window into the fundamental workings of the universe. The energy of certain cosmic rays can exceed even the capabilities of the most powerful particle accelerators on Earth, raising profound questions about the mechanisms responsible for accelerating these particles to such extraordinary energies. Understanding how these particles reach such extreme energy levels is essential for uncovering the deeper processes at work in some of the most extreme cosmic environments. Moreover, the study of cosmic rays extends beyond understanding high-energy phenomena. These particles also serve as tools for exploring the very structure of the universe. By analyzing the behavior and composition of cosmic rays, scientists can glean clues about dark matter, one of the universe's most elusive components. The interactions between cosmic rays and the interstellar medium coupled with the effects of magnetic fields, can reveal hidden information about the matter that fills our galaxy, and even extend to the far reaches of the universe. Cosmic rays also play a significant role in understanding the evolution of both stars and galaxies, influencing galactic dynamics and even potentially impacting the formation of life on Earth. Through their interactions with Earth's atmosphere, cosmic rays might even have a hand in shaping climate patterns, linking the far-flung reaches of space with the environment we inhabit. Thus, the study of cosmic rays not only enriches our knowledge of astrophysical processes, but it also highlights the intricate connections between the cosmos and life on our planet. Another fascinating phenomenon that captivates researchers is the Van Allen radiation belts, which envelop our planet in a field of charged particles trapped by Earth's magnetic field. Discovered in 1958 by James Van Allen and his team, using data from the first American satellite, these belts are predominantly composed of electrons, ions, and protons that originate from the solar wind and cosmic rays. The formation and behavior of the Van Allen belts have raised numerous questions, especially concerning their impact on space weather and Earth's atmosphere. While scientists understand that solar activity can influence the radiation belts, the exact mechanisms responsible for the acceleration of particles within them remain a puzzle. Solar storms, for example, can cause the belts to expand and contract, generating waves that interact with the trapped particles. These interactions can increase the energy of the particles, creating hazardous conditions for both satellites and astronauts. Understanding how these processes unfold is vital to ensuring the safety of space missions and exploring the potential consequences for Earth's atmosphere. A particularly intriguing aspect of the Van Allen belts is the phenomenon of killer electrons. These high-speed electrons, when energized to extreme levels, can pose serious risks to satellite systems and astronauts conducting spacewalks. Researchers are actively working to uncover the triggers behind these sudden surges of dangerous particles, though the unpredictable nature of these events complicates efforts to predict space weather. Additionally, the long-term impact of the radiation belts on Earth's environment is still under investigation. Some speculate that the belts may influence atmospheric chemistry or affect the behavior of satellites in low Earth orbit. As our understanding of the radiation belts continues to deepen, we are uncovering new insights into how these phenomena shape not only our technological capabilities in space, but also the broader cosmic interactions between Earth and the universe. Even more puzzling is the phenomenon of dark flow, an unusual motion detected in galaxy clusters that seems to defy conventional explanations. Discovered in 2008, dark flow refers to the unexpected and large-scale motion of certain galaxy clusters, which appear to be moving in a specific direction at velocities that cannot be entirely explained by the gravitational pull of visible matter within the observable universe. This mysterious motion suggests that there may be gravitational forces at play beyond our current understanding, potentially hinting at massive structures or vast regions of unseen matter that exist beyond the observable universe. The motion of these galaxy clusters could be influenced by unseen superclusters or by the presence of dark matter and dark energy, two invisible components that together constitute most of the universe's mass and energy content. The discovery of dark flow raises important questions about the structure of the universe. Typically, cosmologists explain the motion of celestial bodies by considering the gravitational influence of nearby matter, combined with the overall expansion of the universe. However, dark flow seems to indicate that there are forces acting over far greater distances, perhaps even from structures that lie beyond the boundaries of what we can currently observe. If these galaxy clusters are being influenced by gravitational forces from objects or structures that we cannot directly see or measure, it implies a level of cosmic interconnectedness far deeper than previously thought. As research into dark flow continues, it serves as a reminder of both the vastness and the mysteries that lie beyond our observational reach. With the advent of more advanced technologies, we may soon uncover the answers to these enigmatic phenomena, adding to our understanding of cosmic evolution and the grand, interconnected nature of the universe. One of the most intriguing anomalies in the study of cosmic background radiation is what scientists refer to as the cold spot, an unusually cold patch in the sky that stands out starkly against its surrounding areas. This cold region, significantly cooler than expected, has become the subject of intense debate among researchers, as it suggests that something peculiar might have occurred during the earliest stages of the universe. Some scientists hypothesize that this anomaly could be evidence of a vast supervoid, a massive expanse of space that contains very few galaxies or other matter. Others suggest that it might be a clue to some extraordinary event or influence that took place shortly after the Big Bang, altering the cosmic structure in ways we are still trying to comprehend. In addition to the cold spot, another fascinating enigma arises from the alignment of temperature fluctuations in the cosmic microwave background radiation. These fluctuations, which were expected to be random, show a surprising alignment with the plane of the Milky Way galaxy. This alignment raises significant questions about whether the structure of our galaxy, its stars, dust, and magnetic fields, could be influencing the cosmic radiation that travels across vast distances, from the very edges of the observable universe. Some researchers have proposed that this unexpected alignment might hint at a deeper, more profound connection between our local universe and the larger cosmological environment, potentially pointing to hidden interactions or influences we have yet to fully understand. Equally intriguing is the phenomenon known as hemispherical asymmetry, which refers to the observed differences in the cosmic microwave background between the northern and southern celestial hemispheres. These disparities have prompted cosmologists to propose theories that suggest variations in the density of matter across different regions of the early universe. The possibility that the universe was not evenly distributed during its formative stages challenges conventional ideas about the early inflationary period, a crucial phase in the universe's expansion, and could ultimately force us to reconsider fundamental aspects of cosmological theory. Furthermore, the fluctuations detected in the cosmic background radiation, patterns that deviate from what was predicted by standard cosmological models, offer another set of mysteries that scientists are working tirelessly to unravel. These unexpected variations provide valuable insights into how matter and energy are distributed across the cosmos, yet the observed data often does not align with theoretical expectations. This discrepancy has led many in the field to entertain the possibility that our current models might be incomplete, requiring adjustments or even the introduction of entirely new theories to account for the inconsistencies. These anomalies not only challenge our understanding of the universe, but also open new avenues for investigation, offering fresh opportunities to explore the underlying nature of reality itself. In parallel with the ongoing exploration of these cosmic anomalies, researchers are intensifying their search for extraterrestrial intelligence. Using cutting-edge technology and innovative methods, they are attempting to answer one of humanity's most profound questions: are we alone in the universe? One of the primary tools in this quest is the use of radio telescopes, which scan vast regions of space for signals that might indicate the presence of intelligent life. Known as the Search for Extraterrestrial Intelligence, SETI, this initiative focuses on detecting narrow-bandwidth radio emissions that are often associated with artificial sources, rather than natural phenomena like stars or gas clouds. These efforts have been supported by iconic observatories such as the Arecibo Observatory, once the largest radio telescope in the world, and by a new generation of telescopes specifically dedicated to SETI research. As technology advances, the search for extraterrestrial intelligence is expanding beyond radio waves to include the detection of technosignatures, indicators of advanced technology that might be produced by alien civilizations. Technosignatures encompass a broad range of potential signals, from anomalies in the atmospheric conditions of exoplanets that suggest industrial activity, to the detection of laser emissions or satellite transmissions. The power of modern computers allows scientists to sift through vast amounts of data, searching for these faint but potentially significant signals amid the cosmic noise. An exciting extension of the SETI program is optical SETI, which seeks to identify pulsed light signals that might emanate from extraterrestrial sources. Unlike traditional radio signals, These light bursts could represent an intentional communication attempt, potentially revealing the presence of distant civilizations. By employing both radio and optical methods, scientists are casting a wider net in their search, increasing the likelihood of discovering intelligent life elsewhere in the universe. Notable initiatives like the Breakthrough Listen project, which aims to scan the entire Milky Way galaxy and beyond for extraterrestrial signals, demonstrate the power of collaboration and global effort in advancing this important field of research. As these searches progress, they are not only expanding our understanding of the universe, but are also redefining what constitutes life and intelligence in the cosmos. The discovery of extremophiles, organisms that thrive in Earth's most extreme environments, has significantly altered our perspective on where life might exist. These organisms, found in places like deep-sea hydrothermal vents, highly acidic lakes, and frozen tundras, demonstrate that life can adapt to conditions once thought to be entirely inhospitable. This remarkable resilience suggests that the search for extraterrestrial life might need to expand beyond the narrow parameters of Earth-like conditions, opening the door to a much broader range of possibilities. For example, the discovery of extremophiles in environments with high levels of acidity or salinity has led scientists to consider other worlds where such conditions may exist. Moons like Europa, which orbits Jupiter, and Mars, with its salty brines, are becoming increasingly appealing candidates in the hunt for extraterrestrial life. These environments, characterized by extreme temperatures, high pressure, or radiation, may harbor forms of life that are entirely different from anything we recognize on Earth. The realization that life could thrive in a far wider array of chemical compositions than previously thought is reshaping our approach to astrobiology and guiding our efforts to explore the possibilities of life elsewhere in the universe. The continuing investigation of these cosmic anomalies, combined with the evolving search for life beyond Earth, marks a thrilling chapter in our quest to understand the universe and our place within it. Each new discovery offers a glimpse into the vastness of what we don't yet know and beckons us to look deeper, explore further, and challenge our assumptions about the nature of existence itself. Extremophiles, organisms that thrive in environments once thought inhospitable to life, have ignited a transformative shift in our understanding of the biochemical frameworks necessary for life itself. These remarkable life forms exhibit the capacity to adapt to extreme conditions, ranging from the scorching heat of volcanic vents to the frigid expanses of deep-sea ice, and in doing so, they challenge long-standing assumptions about what defines life. For instance, some extremophiles utilize alternative metabolic pathways, like chemosynthesis, to derive energy from inorganic molecules rather than relying on sunlight. This ability to survive without sunlight has profound implications, prompting researchers to rethink the very nature of life. Could extraterrestrial organisms living in environments that we would consider extreme also survive without sunlight? Might they depend on energy sources unique to their local surroundings, potentially altering the way we search for life in the cosmos? As scientists probe deeper into the universe, the study of extremophiles has expanded the boundaries of what we consider habitable conditions. The idea that life can flourish under what were once considered hostile environments, whether under the crushing pressure of oceanic depths or within the acidic waters of sulfur springs, encourages a broader search for life elsewhere in the universe. No longer are we limited to seeking life only on planets with conditions similar to Earth's. Instead, we are prompted to look beyond our assumptions, broadening the scope of celestial bodies that might support life. This shift has profound implications for the future of space exploration and our hopes of discovering life beyond Earth. The Drake equation, formulated in 1961 by astronomer Frank Drake, provides a framework for considering the vastness of the cosmos and the potential for extraterrestrial life. It asks a deceptively simple question: how many civilizations capable of communicating with us might exist in the Milky Way? By breaking this complex issue down into manageable variables, the Drake equation offers a way to estimate the likelihood of intelligent extraterrestrial life. These 7 key factors, ranging from the rate of star formation to the fraction of planets that might support life, allow scientists to explore the various conditions necessary for life to exist beyond Earth. Each of these variables contributes to a growing understanding of the possibilities for life elsewhere in the galaxy. For instance, planets in the habitable zone of a star, often referred to as the Goldilocks zone, are thought to be the most promising places where life could emerge. This zone is the sweet spot where conditions are neither too hot nor too cold, allowing liquid water to exist, one of the essential ingredients for life as we know it. By studying the rate of star formation and the types of planets that arise around those stars, scientists can refine their predictions about where life might develop. In this way, the Drake equation not only guides our search for extraterrestrial life, but also opens up the imagination, inspiring new hypotheses about what forms life might take under the right conditions. The implications of the Drake equation reach far beyond the realm of science and technology, probing deeper philosophical questions about humanity's place in the universe. As we consider the likelihood of intelligent civilizations elsewhere, we are confronted with profound questions about our own existence. Are we alone in this vast cosmos, or could other intelligent beings share our experience? The question has fascinated humans for millennia and continues to drive research in astrobiology, planetary science, and even philosophy. Moreover, recent advancements in technology have allowed scientists to refine the variables in the Drake equation with greater precision. The discovery of exoplanets, planets outside our solar system, has radically expanded our understanding of the potential for life beyond Earth. Instruments like the Kepler Space Telescope, launched in 2009, have revolutionized our search for exoplanets, uncovering thousands of worlds orbiting distant stars. Among these, scientists have identified numerous planets located in their star's habitable zone, adding new weight to the possibility that life could exist beyond our solar system. Perhaps one of the most exciting revelations from the Kepler mission is the discovery of Earth-sized exoplanets in the habitable zone. Kepler confirmed that many of these planets are not only common, but also likely to have the conditions necessary to support liquid water. In fact, about 1/5 of the stars surveyed by Kepler are known to have at least one Earth-sized planet within their habitable zone. This statistic suggests a vast number of planets where life could emerge, igniting renewed hope and excitement about the potential for finding life elsewhere. As technology advances and our understanding of exoplanets continues to evolve, the search for extraterrestrial life becomes more promising. However, even as we look outward toward distant stars, the questions raised by the discovery of extremophiles and the insights from the Drake equation remind us that the universe is full of mysteries waiting to be unraveled. While we may not yet have definitive answers, the journey of exploration itself brings us closer to understanding not only the potential for life on other worlds, but also the very nature of life itself. Kepler's groundbreaking discoveries have significantly altered our understanding of the potential for life beyond Earth. Through its meticulous observations, Kepler uncovered critical factors that shape a planet's habitability. These factors include the nature of a planet's atmosphere, its size, and its distance from its parent star. Some of the exoplanets Kepler identified are not just Earth-like in size, but they also share characteristics with our own planet, raising intriguing possibilities. These findings suggest that certain planets may have conditions suitable for life. The wealth of data Kepler has provided has encouraged scientists to broaden their thinking, pushing them to reconsider the very conditions required for life, and to explore a wider range of potential habitats than previously imagined. The implications of Kepler's discoveries go far beyond a simple catalog of planets. Each new discovery sparks important questions about the potential for life elsewhere in the universe, fueling the hope that Earth is not the only cradle of life. The search is no longer confined to distant planets orbiting stars within a narrow habitable zone. Scientists now consider a wider spectrum of environments, including those that might harbor microbial life or, potentially, more complex organisms. The data collected by Kepler has transformed the way we think about life in the cosmos, inviting us to imagine the possibility of other civilizations flourishing in distant worlds. The mission's findings also highlight the enduring human quest to understand our place in the universe. With every new planet cataloged, humanity's curiosity and longing to uncover the mysteries of space grow stronger. However, the search for life does not stop at distant planets. Scientists are also turning their attention to moons within our own solar system that might harbor life. A prime example is Europa, one of Jupiter's largest moons, which has long been of particular interest to astrobiologists. Europa is believed to possess a subsurface ocean hidden beneath a thick, icy crust. The ocean is thought to be in contact with a rocky seafloor, a feature that could provide the necessary chemical elements and energy sources needed for life to thrive. This unique environment offers a promising avenue for exploration, with many scientists speculating that Europa may harbor microbial life in its hidden depths. Space missions that utilize powerful telescopes and space probes are vital tools in gathering the information necessary to study this moon's surface and subsurface. Through remote sensing and direct observations, scientists have already begun to identify key features of Europa's surface, including signs of geysers and plumes that eject water vapor into space. These plumes are of particular interest because they contain salts and organic molecules, providing crucial insights into the ocean beneath Europa's icy shell. By analyzing these substances, researchers are able to draw conclusions about the moon's potential to support life. In parallel, laboratory experiments are being conducted to simulate the extreme conditions found on icy moons. These experiments examine how microorganisms from Earth's coldest environments might survive and even thrive under similar pressures and temperatures. This research is essential for understanding the resilience of life and its ability to adapt to extraterrestrial environments. Looking ahead, NASA's Europa Clipper mission, set to launch in the near future, will delve deeper into the mysteries of Europa. This mission aims to conduct an in-depth study of the moon's ice-covered surface and the ocean beneath. With advanced scientific tools, Europa Clipper will measure the moon's geological activity, analyze its ice, and search for essential building blocks of life, such as organic compounds and water. These efforts represent a crucial step in humanity's quest to understand where and how life might exist beyond our planet. As these missions progress, they expand the possibilities for the discovery of extraterrestrial life, particularly in environments once thought too extreme to support living organisms. However, the potential discovery of extraterrestrial life carries significant ethical, philosophical, and socio-political challenges. The implications of such a discovery would not only alter our understanding of life, but also raise critical questions about how we should engage with these alien entities. If intelligent extraterrestrial beings were discovered, what rights would they have? Would they be granted similar protections to the sentient species on Earth, or would they be treated as lesser beings? These questions force humanity to confront its own moral compass and consider the ethical obligations we may have toward these beings. Furthermore, there are concerns about the unintended consequences of such an encounter. The history of human exploration and colonization suggests that contact with radically different civilizations often leads to exploitation, harm, or the spread of harmful pathogens. As humanity ventures into this uncharted territory, it is crucial to proceed with caution and a strong awareness of past mistakes. The potential for miscommunication, exploitation, or even ecological disaster is real. The discovery of intelligent life beyond Earth could also have profound implications for our understanding of human identity and our place in the universe. Such a revelation could challenge long-held religious beliefs, philosophical perspectives, and social structures, forcing us to reevaluate what it means to be human in the grand scheme of the cosmos. Another critical consideration is the role of international cooperation in the event of contact with extraterrestrial intelligence. Such a monumental discovery would require a unified global response. Governments, scientists, and policymakers would need to work together to develop guidelines for responsible exploration and communication. This cooperative approach would be essential to ensure that humanity's interactions with extraterrestrial life are ethical, respectful, and beneficial to all parties involved. The way in which we engage with other civilizations, if and when they are found, will reflect our values and priorities as a species. The Fermi paradox presents an intriguing puzzle in the search for extraterrestrial life. Named after the physicist Enrico Fermi, the paradox highlights the contradiction between the high likelihood of extraterrestrial civilizations existing in our galaxy and the lack of evidence or contact with such civilizations. Given the sheer number of stars in the galaxy, many of which likely have planets that could support life, the question arises, why haven't we encountered any signs of intelligent life? Several theories have been proposed to explain this mystery. One possibility is that intelligent civilizations, while potentially widespread, are exceedingly rare. The conditions required for intelligent life to evolve are extraordinarily specific, involving countless environmental and evolutionary factors that may not often align. Another possibility is that civilizations tend to self-destruct before they can develop the technology to communicate across vast distances. Factors like nuclear war, climate change, or technological collapse could prevent a civilization from surviving long enough to reach out to others. This scenario suggests that while life may be common in the universe, intelligent life capable of communication may be fleeting. As we continue to search the cosmos for signs of life, these questions underscore the complexities of the search for extraterrestrial intelligence. The potential for contact with alien civilizations carries with it both profound scientific opportunities and deep moral responsibilities. The journey to uncover these mysteries will likely challenge our understanding of life, our place in the universe, and what it means to be human. The vastness of space, with its incomprehensible distances, remains one of the most significant obstacles to the search for intelligent life beyond Earth. Even if advanced civilizations exist elsewhere, the sheer remoteness of their locations might prevent us from detecting any signals. Light, which is the fastest thing in the universe, travels at a speed of about 186,000 miles per second. But even at that incredible pace, it takes years or even millions of years to cross the void between stars. A civilization that emerged millions of years ago might only now be sending signals toward us, which could take millennia to reach our planet. Conversely, it's possible that technologically advanced civilizations are intentionally avoiding contact with us. They may choose not to make their presence known for reasons ranging from a desire for solitude to a policy of non-interference, avoiding any influence over less developed societies like ours. Some even hypothesize that the reasons for silence could be far more complex, rooted in a cosmic prime directive, a rule that forbids advanced civilizations from engaging with less evolved species. Moreover, there is the challenge that alien life forms may be so different from what we understand that we would fail to recognize them even if they were right in front of us. Life could exist in forms far beyond our current comprehension, potentially existing in ways that defy our biological and technological assumptions. This challenge is epitomized by the Fermi paradox, which highlights the glaring contradiction between the high probability of extraterrestrial civilizations existing and the complete lack of concrete evidence for their existence. It forces us to confront our limited understanding of what constitutes life and intelligence, pushing us to rethink the very nature of existence itself. How could we identify something so fundamentally alien when we have so little understanding of what is possible? Throughout history, a few tantalizing signals have sparked widespread curiosity and speculation about extraterrestrial technology. One of the most notable occurrences was the WOW signal in 1977. This strong, narrowband radio signal was recorded by a researcher using the Big Ear radio telescope at Ohio State University. The signal, which lasted for just 72 seconds, came from the direction of the constellation Sagittarius. Its characteristics suggested that it could have originated from an extraterrestrial source. Despite repeated efforts to detect the signal again, it has never been observed a second time. This mysterious event has left scientists wondering whether it was a one-time transmission from an alien civilization or if we are simply missing a broader, more consistent signal. In addition to the WOW signal, scientists have continued to observe other puzzling phenomena. For example, fast radio bursts, FRBs, are brief, intense flashes of radio energy detected from deep space. Some of these bursts can be attributed to known astrophysical processes, such as collapsing stars or magnetized neutron stars. However, a small number remain unexplained, leading to speculation that they could be the result of artificial sources, perhaps even signals from distant advanced civilizations. Each new discovery of FRBs fuels ongoing research into their origins as scientists consider the possibility of extraterrestrial technology at play. The search for life beyond our planet has been significantly invigorated by the study of exoplanets, planets that orbit stars outside our solar system. A breakthrough in this field came when astronomers discovered planets within their star's habitable zones. These are regions where the conditions might be just right for liquid water to exist on a planet's surface, a key ingredient for life as we understand it. As a result, the hunt for extraterrestrial signals has taken on new urgency. Projects like SETI, Search for Extraterrestrial Intelligence, have evolved, leveraging advanced technology to sift through vast amounts of data, actively searching for any sign of artificial signals from the stars. Data from observatories like the Kepler Space Telescope has dramatically expanded our catalog of exoplanets. Thousands of planets have now been identified in the so-called habitable zones of their stars, some of which have similarities to Earth. This growing inventory of potentially habitable worlds has made the search for extraterrestrial signals all the more enticing. The discovery that there could be millions of planets in our galaxy with the right conditions for life has raised the possibility that we may not be alone in the universe after all. The discovery of exoplanets has completely reshaped our thinking about the potential for life beyond Earth. These planets, found in the Goldilocks zone, the region around a star where conditions are not too hot and not too cold for liquid water to exist, are particularly fascinating. Liquid water is a critical factor in the development of life as we know it, so these exoplanets are now at the center of astrobiological research. Until recently, the search for extraterrestrial life was based largely on speculation, relying on our limited knowledge of our own solar system. But with the discovery of thousands of exoplanets, many of which reside in habitable zones, our understanding of what is possible has expanded exponentially. As astronomers continue to uncover more exoplanets, they are also studying their atmospheres for chemical signatures that might indicate the presence of life. Gases like oxygen, methane, or carbon dioxide could suggest biological activity, providing vital clues about whether these planets might harbor life. The 500 exoplanets now known to reside in habitable zones challenge long-standing theories about where life can exist. These planets force us to expand our definition of habitable environments and to consider the possibility that life could exist in forms we have yet to imagine. This shift in perspective is both inspiring and humbling, fueling a renewed interest in astrobiology and captivating the public's imagination. The mere existence of these exoplanets encourages us to rethink our place in the cosmos. Instead of seeing ourselves as solitary inhabitants of a barren, empty universe, we are beginning to see ourselves as part of a broader, more interconnected cosmic ecosystem. This shift in perspective brings a new sense of hope and possibility. The hope that one day we may find evidence of life beyond Earth. Interstellar exploration is also pushing humanity's frontiers. Missions like the Voyager spacecraft, which were launched in the late 1970s, are pushing the boundaries of our solar system and venturing into interstellar space. Their primary mission has been to gather data about the heliosphere, the vast region of space influenced by the solar wind emitted by the sun. But the Voyagers have also begun to collect invaluable information about cosmic rays and magnetic fields that exist beyond the influence of our sun. As these spacecraft journey further into the unknown, they provide us with precious insights into the origins of cosmic phenomena and the conditions that exist far beyond the confines of our solar system. These missions are helping us to better understand the nature of the universe, and who knows, perhaps they will one day lead us to answers about extraterrestrial life. One of the most formidable challenges in space exploration is the immense distance between stars. The vastness of the cosmos is almost beyond comprehension. Even at the incredible speeds achieved by the Voyager spacecraft, it would take more than 70,000 years to reach the nearest star to our solar system, Proxima Centauri. This staggering time frame is a constant reminder of the scale of the universe and the challenges that lie ahead for humanity in its quest to explore the stars. For scientists and engineers, this vast distance raises profound questions. How long can spacecraft survive on these multi-millennial journeys? Will they be able to collect meaningful data and transmit it back to Earth across such unthinkable spans of space and time? Currently, communication with spacecraft like Voyager is facilitated by radio signals, which travel at the speed of light. However, even at this remarkable speed, the time lag is significant. It takes over 20 hours for a signal to travel from Voyager to Earth, meaning that any data collected must wait over a full day before it can be analyzed. This delay complicates not only the gathering of data, but also the interpretation and real-time decision-making necessary for extended space missions. The sheer scale of space itself becomes a kind of filter, forcing us to rethink how we approach everything from communication to mission design. In addition to the daunting distances, the hostile environment of outer space adds another layer of complexity. The extreme temperatures, pervasive radiation, and the constant threat of micrometeoroid impacts make space an unforgiving arena for any spacecraft. The materials and technologies used in space exploration must be built to endure these conditions over extremely long periods. For example, the Voyager spacecraft rely on radioisotope thermoelectric generators, which convert the heat released by radioactive decay into electricity to power their instruments. However, as time goes on, these power sources gradually diminish, and the spacecraft's capabilities shrink. Eventually, there will come a time when even the most durable spacecraft will have to cease operations because they can no longer generate the power necessary to continue their mission. In light of these challenges, future space missions demand a new kind of thinking, innovative technologies that push the boundaries of what is possible. Concepts such as solar sails, which harness the pressure of sunlight to propel spacecraft, or advanced propulsion systems that use the gravity of stars for slingshot maneuvers, are being explored to increase travel speeds and improve mission efficiency. These technologies may hold the key to faster, more efficient space travel and could one day allow humanity to explore the stars with a fraction of the time it currently takes. The lessons learned from ongoing missions like Voyager are not just a record of human achievement, but a roadmap that will guide future generations of space explorers. The obstacles faced by current missions will fuel the next wave of advancements in space travel and technology, enabling humanity to push further into the unknown. Simultaneously, the James Webb Space Telescope, often referred to simply as Webb, stands on the brink of transforming our understanding of the universe. Set to operate primarily in the infrared spectrum, Webb can observe celestial objects that are too faint or too distant for other telescopes to detect. By studying the cosmos in these longer wavelengths, Webb offers a glimpse into the earliest moments of the universe, capturing light from stars and galaxies that formed shortly after the Big Bang. This ability to peer deep into the distant past could help us understand not just the origins of individual stars and galaxies, but the entire structure and evolution of the universe itself. One of the key areas where Webb will make groundbreaking contributions is in the study of star and planetary system formation. Its advanced instruments are designed to capture the faint glow of newly forming stars, offering insights into the complex processes that take place within clouds of gas and dust. This could provide clues about the formation of our own solar system and other planetary systems in the galaxy. By analyzing these stars and their environments, scientists will gain a deeper understanding of the forces that shape planetary formation. Another exciting frontier for Webb is its ability to study exoplanets, planets that exist outside our solar system. Over the past few decades, astronomers have discovered thousands of exoplanets, and Webb will take this search to new heights. By observing the starlight that filters through an exoplanet's atmosphere during its transit across its host star, Webb can detect chemical signatures that reveal the composition of the atmosphere. This could help scientists assess whether conditions exist that might support life. The potential for discovering habitable environments beyond Earth has never been more tangible, thanks to Webb's incredible capabilities. Beyond exoplanets, Webb will also enhance our understanding of galaxy formation and evolution. The telescope's ability to observe distant galaxies will allow scientists to piece together the history of these massive structures, uncovering clues about how they formed and grew over billions of years. With its unprecedented ability to capture light from the faintest objects in the universe, Webb will shed new light on some of the oldest and most distant galaxies, offering a clearer picture of the universe's evolution. The James Webb Space Telescope represents a leap forward in our ability to observe and understand the cosmos. It will open new doors to discoveries that could redefine our understanding of space, time, and the origins of life itself. As we peer deeper into the universe, we are bound to uncover new mysteries that will inspire future generations of explorers to continue their quest for knowledge. In 2006, the New Horizons spacecraft was launched on a mission to explore the outer reaches of our solar system, making history in 2015 when it conducted a flyby of Pluto. The images returned by New Horizons showed Pluto to be a far more complex and varied world than scientists had ever imagined. The icy surface, with its towering mountains, vast plains, and even a heart-shaped region named Tomball Regio, challenged our preconceived notions about this distant world. The discovery of geological activity on Pluto was a stunning revelation, demonstrating that even the most distant and seemingly static objects in the solar system could be more dynamic than we thought. After its encounter with Pluto, New Horizons pressed on toward the Kuiper Belt, a region beyond Neptune that contains icy bodies and remnants from the early solar system. In 2019, the spacecraft performed a flyby of a distant object known as Arrokoth, formerly Ultima Thule, revealing it to be a unique contact binary, a structure made up of two lobes that had fused together. This discovery provided scientists with a glimpse into the building blocks of planetary formation, offering clues about how our solar system, and possibly others, began to take shape. New Horizons also made contributions to our understanding of cosmic phenomena, such as the composition of Pluto's atmosphere and surface. It detected hazes in the atmosphere, as well as organic molecules and nitrogen frost covering the surface. These findings sparked new discussions about the potential for atmospheres and climates on other worlds, expanding the scope of astrobiology research. The knowledge gained by New Horizons has profound implications for our understanding of planetary science, revealing the processes that govern the evolution of celestial bodies and offering new insights into the forces that shape our solar system. Through its exploration of the Kuiper Belt, New Horizons has also provided valuable data that will help map this vast and largely unexplored region of space. Each discovery made by the spacecraft not only deepens our understanding of Pluto and its neighbors, but also adds to the broader picture of planetary science. These findings will continue to inspire future missions and help refine our understanding of where we fit within the grand scheme of the cosmos. At the heart of all these missions lies a remarkable level of collaboration between international space agencies. By pooling resources, expertise, and technology, nations can tackle the ambitious challenges posed by space exploration. Whether it's missions to distant planets, building large space telescopes, or developing new propulsion systems, teamwork allows for more ambitious goals and increases the likelihood of success. Each space agency brings its unique strengths to the table. NASA, with its history of manned spaceflight, the European Space Agency, known for its advanced satellite programs, and others that contribute their specialized knowledge. Together, they form a collective force capable of achieving far more than any single nation could alone. This global cooperation has not only made space exploration more feasible, but has also led to the development of new technologies and methodologies that might never have emerged in isolation. By combining their efforts, space agencies are shaping the future of space exploration and pushing humanity closer to its ultimate goal of understanding and exploring the cosmos. With each new mission and discovery, the possibilities for what we can achieve in space become more exciting and more profound. The future of space exploration is truly a global endeavor, and together we will continue to unlock the secrets of the universe. International partnerships are a powerful force in uniting countries in the shared pursuit of understanding our universe. One of the most notable examples of such collaboration is the International Space Station, ISS, which serves as a testament to what can be achieved when nations set aside their differences to work together for the common good. The ISS is not just a platform for scientific research. It is a symbol of how cooperative ventures can foster scientific exchange and expand humanity's collective knowledge. Scientists from across the globe engage in open dialogue, share their findings, and conduct experiments that transcend national borders. Moreover, the diplomatic relationships formed through these international collaborations help promote the peaceful use of outer space. By fostering partnerships and maintaining open lines of communication, countries can address challenges, resolve disputes, and ensure the ethical exploration of the cosmos. The ISS, for example, plays a crucial role in demonstrating that space exploration need not be a competitive race, but can instead serve as a unifying force. It encourages a collaborative spirit that extends beyond scientific achievements, inspiring future generations to dream of a shared cosmic destiny, where humanity's efforts are aligned toward a common goal. The technological advancements that have emerged from these collaborative ventures have revolutionized our ability to explore the cosmos in unprecedented ways. One of the most significant breakthroughs in space exploration is the development of advanced propulsion systems. Traditional chemical rockets, once the primary method for launching spacecraft, have been complemented and enhanced by innovations such as ion propulsion and electric thrusters. These advanced propulsion methods utilize electric energy to accelerate ions, producing thrust more efficiently than conventional rockets. This technology has the potential to propel spacecraft to distant outer planets and even interstellar space, opening new avenues for exploration far beyond the confines of our solar system. Another area where innovation has had a profound impact is in imaging and sensor technology. High-resolution cameras and spectrometers have become essential tools for modern space missions. These sophisticated instruments allow scientists to capture stunning images and gather invaluable data from distant celestial bodies. For instance, the Hubble Space Telescope and the James Webb Space Telescope use these advanced tools to observe galaxies billions of light years away and to identify exoplanets in distant star systems. Their ability to analyze light across various wavelengths not only enhances our understanding of the universe's origins, but also provides insights into the potential habitability of distant worlds. These technological strides are transforming the way we look at the universe and guiding future explorations in the search for life beyond Earth. Robotic exploration has also undergone a revolution. Today's autonomous systems are capable of performing complex tasks without direct human intervention, making missions more efficient and safer. Rovers like Curiosity and Perseverance on Mars are prime examples of this advancement. These robots are equipped with artificial intelligence, enabling them to make decisions on the fly as they navigate challenging terrain and conduct experiments. This ability to act autonomously allows for greater flexibility in exploration, ensuring that these rovers can continue to operate even in the most inhospitable environments. By operating without constant human oversight, these robots reduce the need for delays in decision-making and enable faster progress in exploring other planets. Moreover, advancements in communication technology have greatly improved the way we transmit data from space back to Earth. Enhanced radio frequency systems and laser communications now allow for faster data transfer, making it possible for scientists to receive and analyze information in real time. This improvement means that discoveries made in the farthest reaches of space can be communicated back to Earth almost immediately, accelerating the pace of scientific research and enhancing our understanding of the universe. These technological advancements are not just about pushing the boundaries of space exploration. They are opening doors to more comprehensive and in-depth explorations of our solar system and beyond. Robotic missions, in particular, are laying the groundwork for future human exploration of Mars. By sending unmanned spacecraft to the Red Planet, scientists are able to gather crucial data on its surface, atmosphere, and resources. These missions provide insights into the planet's radiation environment, soil composition, and potential for sustaining human life in the future. One of the most important contributions of robotic missions to Mars exploration is the search for water. The discovery of ancient river valleys and polar ice caps on Mars, such as those observed by the Mars Reconnaissance Orbiter, has indicated that liquid water may have once flowed across the planet's surface. Water is a vital resource for any future human mission to Mars, as it will be necessary not only for drinking, but also for producing oxygen and fuel. The ability to identify and map water sources will be critical for planning future manned missions. With this knowledge, future astronauts could have access to water that could be used for life support and fuel production, which will be essential for long-duration missions. Robots like the Perseverance rover are also testing new technologies that could be used by humans on Mars in the future. For example, Perseverance is experimenting with a technique called atmospheric oxygen production, which involves converting carbon dioxide into oxygen, a process that could be vital for sustaining human life on Mars. This breakthrough technology could one day allow astronauts to generate the oxygen they need to survive on the Martian surface, significantly reducing the need to transport oxygen from Earth. In addition to these life support systems, robotic missions are providing critical information about Mars's environment and weather patterns. By studying phenomena such as dust storms, temperature fluctuations, and atmospheric conditions, scientists can design habitats that are capable of withstanding the harsh Martian climate. The data gathered from these missions allows for more effective planning of human activities on the surface, from daily routines to long-term settlement strategies. Each successful robotic mission brings humanity one step closer to sending humans to Mars. These missions not only help mitigate the risks associated with human space exploration, but also refine our understanding of what it will take to live and work on another planet. The knowledge gained from these robotic explorers will form the foundation of future human missions to Mars, helping us unlock the mysteries of the Red Planet and ultimately achieve the dream of sending humans to the surface of another world. In the farthest reaches of the cosmos, pulsars act as celestial lighthouses, emitting beams of radiation that sweep across space with astonishing precision. These highly magnetized, rotating neutron stars send out regular pulses of electromagnetic radiation, often in the form of radio waves. The consistency of these pulses makes pulsars incredibly valuable tools for astronomers who use them as cosmic clocks to navigate the vast distances of space. By measuring the timing of these pulses, scientists can determine the distance and orientation of pulsars in the galaxy with remarkable accuracy. The rhythmic pulses emitted by pulsars can be detected from great distances, and their precision allows astronomers to map the universe with incredible detail. As a pulsar spins, its beams of radiation sweep across space like a lighthouse beacon. And if Earth lies in the path of these beams, we receive a signal that appears to pulse at regular intervals. By analyzing these signals, scientists can gain insight into the fundamental properties of the pulsar, its distance from Earth, and its position in the galaxy. This ability to measure cosmic objects with such accuracy has the potential to revolutionize space navigation and our understanding of the structure and dynamics of the universe. Together, these advancements in technology, international collaboration, and robotic exploration are driving humanity's quest to explore the cosmos. As we continue to push the boundaries of space exploration, these breakthroughs are bringing us closer to a future where we can answer some of the most profound questions about the universe, the origins of life, and our place in the cosmos. Pulsars, which are rapidly rotating neutron stars emitting beams of electromagnetic radiation, play an essential role in the broader network of celestial navigation known as the Pulsar Timing Array. This sophisticated system interconnects multiple pulsars, creating a vast framework that allows scientists to monitor the position and movement of objects across space with remarkable precision. By analyzing the steady and regular pulse signals from these cosmic beacons, researchers can track spacecraft trajectories with pinpoint accuracy, even gauging the gravitational effects exerted by massive celestial bodies. This method of using pulsars as reference points for navigation opens up the possibility of interstellar travel, where future spacecraft may rely on these pulsars to chart their course across the vast distances between stars, ensuring they reach their destinations with a degree of precision previously thought impossible. This innovative approach underscores the versatility of pulsars, transforming them from mere astrophysical phenomena into crucial tools for humanity's ongoing exploration of the cosmos. In parallel, Unmanned probes have revolutionized our understanding of comets, asteroids, and the broader solar system, uncovering a wealth of discoveries that challenge our previous conceptions of these ancient celestial bodies. One of the most groundbreaking revelations came from the Rosetta mission, which studied the comet 67P Churyumov-Gerasimenko. By closely examining the comet's surface and composition, scientists found complex organic molecules, reinforcing theories about the origins of life on Earth. This finding is particularly striking because it suggests that organic compounds, which were once thought to be exclusively terrestrial, may have been delivered to our planet from space. It challenges traditional assumptions about the exclusive role of Earth in the development of life and opens up new avenues for considering how life may exist elsewhere in the universe. Meanwhile, the study of asteroids has provided equally astonishing insights. NASA's Near Shoemaker mission, which examined the asteroid Eros, revealed the presence of minerals that could only have formed in the presence of water. Similarly, the Hayabusa probe returned samples from the asteroid Itokawa, uncovering further evidence of water-rich materials. These findings suggest that asteroids may not be barren, lifeless rocks, but rather hold vital clues about the early conditions of our solar system and the formation of planets. In fact, asteroids may even serve as reservoirs of essential elements for life, offering a new perspective on the potential for extraterrestrial life and the processes that led to the emergence of our own planetary system. Moreover, the Deep Impact mission, which bombarded the comet Tempel 1 with a projectile, provided new insight into the internal structure of comets. The explosion caused a violent outgassing, which revealed that comets are not monolithic, static objects, but rather dynamic, layered bodies. These findings indicate that comets are not only remnants of the solar system's formation, but also active entities that evolve over time. Such revelations have led to a reevaluation of planetary defense strategies. By understanding the composition and orbits of near-Earth objects, scientists can predict potential impacts and devise more effective ways to mitigate risks posed by these cosmic wanderers. Each new discovery from these unmanned probes brings us closer to unraveling the complex history of our solar system, revealing celestial bodies teeming with secrets and potential. Meanwhile, advanced telescopic technologies are enabling scientists to peer further back in time toward the birth of the universe itself. With tools like the Hubble Space Telescope and the James Webb Space Telescope, researchers are able to observe light from galaxies and stars that have been traveling through space for billions of years, providing a glimpse into the early moments of the universe. This ancient light is crucial to understanding the conditions that existed shortly after the Big Bang, roughly 13.8 billion years ago, and the formation of the first atoms and elements that eventually led to the creation of stars, planets, and life as we know it. In addition to these space-based observatories, radio telescopes have become invaluable in the quest to understand the universe's origins. By observing the cosmic microwave background radiation, an afterglow of the Big Bang, astronomers can map the subtle variations in this radiation, revealing the density fluctuations that were responsible for the formation of galaxies and large-scale structures. These fluctuations tell the story of the universe's evolution from its earliest moments, providing critical clues about the forces that shaped the cosmos. The ability to detect these faint signals from the far reaches of space is central to constructing a detailed picture of the universe's birth and growth. Through this intricate web of telescopic technologies, scientists are piecing together a comprehensive narrative of the universe's early days. With each new discovery, they uncover another layer of understanding about how the universe expanded from a singular point, the Big Bang, and how the elements that make up everything we know came into existence. This journey into the deep past not only helps answer fundamental questions about the cosmos, but also provides insight into the very nature of reality itself. Superclusters, the enormous groupings of galaxies that represent the largest structures in the universe, are key players in shaping the cosmic landscape. These superclusters exert a powerful gravitational influence on the galaxies within them, dictating the structure of the cosmic web, a vast network in which galaxies are not scattered randomly, but rather aligned in a filamentous pattern, with superclusters forming the nodes of this web. The study of superclusters is vital to understanding the large-scale structure of the universe and the underlying forces that shape it. They provide crucial evidence for the existence of dark matter and dark energy, mysterious substances that play a fundamental role in the expansion of the universe. One notable example is the Laniakea supercluster, which encompasses our own Milky Way galaxy, along with countless other galaxies and smaller clusters. By studying the formation and evolution of superclusters like Laniakea, astronomers gain valuable insights into the dynamics of cosmic evolution and the forces that have shaped the universe over billions of years. The gravitational pull of superclusters continues to play a central role in the ongoing formation of galaxies, highlighting the dynamic and interconnected nature of the cosmos. These vast structures also provide a deeper understanding of the universe's organization, showing that the distribution of galaxies is not the result of random processes, but instead follows a fundamental pattern governed by gravity. The presence of superclusters offers a glimpse into the very architecture of the universe, suggesting that large-scale cosmic structures are not only formed by the forces of gravity, but also reflect the deep underlying principles that govern the cosmos. Through the study of these colossal groupings of galaxies, we gain a better understanding of the universe's past, present, and future, and our place within it. Superclusters, the vast collections of galaxy clusters, hold an extraordinary key to understanding the cosmos. These colossal structures where galaxies gather and interact reveal much more than just the grouping of stars. They provide vital insights into the forces shaping the formation of galaxies and the intricate interplay between them. Observing superclusters not only helps to decode the early universe, but also sheds light on how matter is distributed across vast distances, an essential component of our understanding of cosmic evolution. Linking these cosmic phenomena to contemporary theories offers a clearer view of how the universe unfolded, deepening our understanding of its past, while also giving us a glimpse into its future. The discovery of rogue stars, isolated travelers drifting through space without any home galaxy, opens another chapter in this cosmic narrative. These stars have been ejected from their original galaxies, often due to extreme gravitational interactions with black holes or massive stellar objects. Studying rogue stars allows astronomers to piece together the dynamic processes that govern the formation and destruction of galaxies. Their existence offers clues about the violent history of their parent galaxies, suggesting violent events like supernova explosions or collisions with dense star clusters. These solitary wanderers not only reveal the cataclysmic forces that shape the destiny of individual stars, but they also provide insight into the overall structure of the galaxies from which they were cast out. The process of ejection itself is a significant clue to the turbulent environments within galaxies. Moreover, by tracking the movement of rogue stars, we can learn more about the complex histories of galactic mergers, how galaxies collide, merge, and evolve over time. Rogue stars even offer tantalizing hints about the elusive nature of dark matter. Their trajectories can act as markers, showing how dark matter's gravitational effects shape the cosmos. As these stars wander through space, they enrich our understanding of galactic dynamics and the unseen forces that govern the universe. This study of rogue stars plays an essential role in expanding our comprehension of the chaotic processes that govern star formation and evolution. It also reveals how the remnants of cataclysmic events continue to influence the structure of galaxies today. In uncovering the stories of these lone wanderers, astronomers are unraveling the deeper mysteries of how galaxies and the stars within them are shaped by forces beyond our immediate comprehension. Another pivotal piece of evidence for the existence of dark matter comes from the fascinating phenomenon known as gravitational lensing. When light from distant galaxies passes near an enormous object like a galaxy cluster, the intense gravitational pull of that cluster bends the path of light. This bending creates distorted or magnified images of the distant galaxies behind it. But when scientists analyze these distortions, they find that the amount of bending far exceeds what could be caused by the visible mass within the cluster. This discrepancy strongly suggests the presence of a significant amount of unseen mass, dark matter, that is warping space-time and influencing the way light travels across the universe. Additionally, the motion of galaxies within these clusters provides further confirmation of dark matter's existence. By measuring the speeds at which galaxies orbit the center of a cluster, scientists have discovered that there is far more mass present than can be accounted for by the visible matter alone. The galaxies move too quickly to be held together by the gravity of only the visible stars and gas. This imbalance points to the presence of dark matter, which fills in the gaps where visible matter cannot provide enough gravitational pull. The study of these galaxies and their motions helps map the gravitational influence of dark matter, offering profound insights into its pervasive role in shaping the universe. The distribution of hot gas within galaxy clusters provides yet another layer of evidence for dark matter. By examining the temperature and density of this gas, scientists find that the gravitational forces holding the gas in place are far stronger than those exerted by the visible matter alone. These forces are likely due to dark matter, which contributes to the overall gravitational well of the cluster, preventing the hot gas from escaping into intergalactic space. Without dark matter, the gas would likely disperse, offering further evidence of its crucial role in maintaining cosmic structures. Moreover, the cosmic microwave background, CMB, radiation, an ancient remnant of the Big Bang, offers broader insight into the universe's makeup. Measurements of the CMB show fluctuations that correlate with the distribution of both visible and dark matter in the early universe. These fluctuations match the density of dark matter, providing a universal context for understanding its role in the formation of galaxies and galaxy clusters. Taken together, these multiple lines of evidence form a compelling case for the existence of dark matter, fundamentally altering our understanding of the universe. Galaxy mergers are yet another critical event in the life cycle of galaxies, offering rich insights into their evolution. When galaxies collide, their structures can be dramatically altered. Star formation often surges as clouds of gas are compressed under intense gravitational forces, leading to the creation of new stars at unprecedented rates. These mergers reveal much about the conditions under which galaxies form new stars, deepening our understanding of the forces that dictate the life cycles of galaxies. Moreover, studying these mergers helps astronomers understand how galaxies grow and evolve over time, as well as the role of dark matter in this process. During a merger, galaxies interact in complex and fascinating ways. Their gas and stars collide, triggering bursts of star formation and reshaping the galaxy's overall structure. This dynamic interaction provides a window into how galaxies change over time and how new stars are born from the remnants of cosmic collisions. Additionally, the merger process amplifies the gravitational influence of dark matter, helping scientists infer its distribution and behavior in the universe. By observing how dark matter halos merge and interact, researchers are gaining valuable insights into the fundamental forces that shape the structure of the cosmos. Each of these phenomena, from rogue stars to gravitational lensing, galaxy mergers, and the ever-present influence of dark matter, paints a richer picture of the universe. Together, they form a complex and interconnected narrative, shedding light on how galaxies evolve, how stars form and die, and how the unseen forces of dark matter shape the very fabric of space and time. With each discovery, we uncover more about the forces that govern the cosmos, bringing us closer to understanding our place within this vast, ever-changing universe. In the vastness of the universe, one of the most fascinating and enigmatic processes is the transformation of galaxies. Over time, galaxies evolve, shifting from distinct spiral shapes to more irregular, often chaotic structures. These changes are not random. They offer profound insights into the nature of galactic development and in the intricate mechanics that have shaped the cosmos over billions of years. By examining various epochs of galactic mergers across the universe, researchers are slowly piecing together a comprehensive narrative of galactic formation, evolution, and the forces that govern them. When galaxies come into close proximity with one another, their gravitational fields begin to interact in ways that dramatically alter their structures. The effects of these gravitational forces are varied, ranging from subtle distortions to complete transformations. One of the most striking phenomena to emerge from these encounters is the formation of tidal tails, long streams of gas and stars that stretch across space for light years. These tales are not just fascinating visual features, they are key to understanding the complex dynamics of galaxy interactions. They offer clues about how galaxies influence one another, shaping their evolution in ways we are only beginning to understand. The aftermath of these interactions often triggers an explosion of star formation. When galaxies collide or pass close to each other, their interstellar gas can be compressed. This compression creates dense regions where new stars are born at rates far higher than typical. These bursts of star formation raise important questions about the underlying processes that drive such dramatic changes in galactic environments. Scientists are eager to determine whether these bursts have long-lasting effects on the growth and evolution of the galaxies involved, or whether they represent brief, intense phases in a galaxy's life cycle. Another intriguing aspect of these galactic interactions is the effect they can have on active galactic nuclei, AGN. As two galaxies engage in their cosmic dance, material can be funneled into the supermassive black holes that lie at their centers. This influx of material can cause the black holes to become highly active, emitting vast amounts of energy and light. In some cases, this results in the transformation of an otherwise quiet galaxy into a brilliant quasar. The study of these active galactic nuclei is critical for understanding the life cycle of galaxies and the evolution of their central black holes. As these black holes grow and interact with their surroundings, they play a pivotal role in the overall development of the galaxy. Ultimately, the after effects of gravitational interactions between galaxies remain one of the most exciting and mysterious areas of astronomical research. Each encounter offers a unique set of circumstances, providing new insights into how galaxies can influence one another over vast cosmic timescales. The complexity of these interactions challenges our current understanding of galactic dynamics, offering a more detailed view of how the universe itself has evolved. As our research continues, we are likely to uncover deeper connections between individual galactic encounters and the broader cosmos, revealing an intricate web of relationships that shape the universe's history. Different types of galaxies, spiral, elliptical, and irregular, offer valuable insights into the cosmic life cycle. Spiral galaxies, with their signature spiral arms, are often rich in gas and dust. This abundance of material fuels the ongoing birth of new stars, making them dynamic and vibrant environments. The constant formation of stars in these galaxies suggests that they are prime candidates for harboring life, as they possess the ingredients necessary for the emergence of habitable planets. These galaxies represent the more youthful, active phase of galactic evolution, where the forces of creation are at their peak. In contrast, elliptical galaxies paint a different picture. They are typically composed of older stars with little to no gas and dust. This lack of raw material for star formation indicates that elliptical galaxies may have already exhausted their ability to create new stars. The environment in these galaxies is quieter, less dynamic. As a result, they may not be able to support the conditions necessary for life as we know it. Instead, elliptical galaxies may offer a glimpse into an earlier phase of the universe where stars were born, lived, and died without the constant creation of new generations. Irregular galaxies, which lack the defined structure of spiral or elliptical galaxies, are often the result of gravitational interactions or mergers with other galaxies. These galaxies are chaotic in nature, and their irregular shapes reflect the tumultuous history of their formation. Despite their disorderly appearance, irregular galaxies are not without their own forms of beauty. They are hotbeds of star formation, with sporadic bursts of new stars appearing throughout their lifespan. These bursts, while not as consistent as those in spiral galaxies, provide a glimpse into the processes that can lead to the creation of planets and potentially life. The diversity of these galaxies underscores the many pathways through which life might emerge in different cosmic environments. By studying the various types of galaxies, scientists gain valuable insights into the history of star formation, the distribution of elements necessary for life, and the potential for habitable planets. Each galaxy type offers a unique perspective on how the universe evolves and how life might emerge in distant corners of the cosmos. This knowledge not only enhances our understanding of galactic evolution, but also deepens our awareness of the possibilities for life beyond Earth. One of the most profound discoveries in recent years has been the identification of ancient galaxies that formed only a few 100 million years after the Big Bang. These early galaxies challenge existing theories about the timeline of cosmic evolution. They reveal that stellar formation and the development of galactic structures began much earlier than previously thought. This discovery suggests that the processes governing galaxy formation are far more efficient than our models had predicted. Ancient galaxies often exhibit complex structures, indicating that they were not simple collections of stars, but rather intricate systems shaped by mergers, interactions, and the influence of dark matter. These findings are reshaping our understanding of how galaxies formed and evolved in the early universe. As astrophysicists reassess their theories, these ancient galaxies are prompting revisions in our models of cosmic evolution. The result may be a more nuanced understanding of the forces and conditions that governed the birth of galaxies, and by extension, the birth of the universe itself. In summary, the study of galaxies, their interactions, and their evolution over cosmic timescales provides a window into the forces that have shaped the universe. By examining these celestial bodies, scientists are piecing together a detailed history of the cosmos, one encounter at a time. The more we learn, the more we come to realize that the universe is not just a collection of isolated systems, but an intricate, interconnected web of relationships, each galaxy playing a crucial role in the ongoing story of cosmic evolution. The discovery and analysis of ancient galaxies is one of the most exciting frontiers in modern astronomy, as it provides invaluable insights into the early universe and the cosmic processes that led to the formation of stars, galaxies, and the very elements necessary for life. When scientists detect these ancient galaxies, they are essentially peering back in time, unlocking clues to the conditions that enabled the first stars to form. These early stars played a crucial role in the enrichment of the universe's chemical makeup, releasing heavy elements into the surrounding space. This enrichment process laid the foundation for the creation of planets, and ultimately, for the emergence of life as we know it. This link between ancient galaxies and the formation of life on Earth underscores their profound influence on the evolution of the universe, not just in the creation of other celestial structures, but in shaping our own existence. As researchers continue to probe these ancient galaxies, they are building a detailed, dynamic timeline of the cosmos, unraveling the complexities of cosmic history. With each new discovery, a new piece of the universal puzzle is added, helping us understand the grand narrative of the universe, where past events continuously shape the present and future. The past is not just history. It is a living force that shapes the unfolding cosmic landscape, driving the universe's evolution forward. One area where this ongoing exploration yields remarkable insights is in the study of the galactic center. The center of our galaxy, the Milky Way, offers a unique environment that provides astronomers with an extraordinary opportunity to study the processes that govern star formation. The galactic center is densely packed with stars and encircled by vast clouds of gas and dust, which are the essential ingredients for new stars to form. Within this environment, astronomers are able to witness the intricate interactions between gravity, gas dynamics, and stellar evolution. The gravitational forces in this region are extraordinarily strong, creating an environment where rapid star formation is common. In fact, researchers have observed the birth of young, massive stars within the galactic center, offering vital clues about the conditions that encourage star formation. One of the most important factors is the presence of molecular gas, which is required in the early stages of star creation. Without this gas, the process of star formation cannot even begin. Understanding how this molecular gas accumulates, interacts, and eventually leads to the birth of stars is key to deciphering the broader mechanisms of stellar creation. Furthermore, the study of the galactic center provides essential insights into how stellar feedback influences star formation. When massive stars are born, they often generate powerful stellar winds and sometimes even undergo explosive supernova events. These phenomena release enormous amounts of energy, which can disrupt the surrounding gas and dust clouds. In some cases, this disruption leads to the formation of new stars, while in others, it can halt the process of star formation altogether. Understanding these feedback processes at the galactic center help scientists piece together the complex and often chaotic narrative of how stars come into being, not just in our galaxy, but across the entire cosmos. With the advent of advanced telescopes and cutting-edge observational techniques, astronomers are beginning to unlock the mysteries of star formation at the heart of the Milky Way. By observing various wavelengths of electromagnetic radiation, including infrared and radio emissions, scientists can peer through the dense clouds of dust that typically obscure our view. These wavelengths have the ability to penetrate the dust, revealing star-forming regions that would otherwise be hidden from view. This ability to see beyond the veil of dust is crucial to understanding both the evolution of our galaxy and the larger-scale processes of star formation that occur throughout the universe. At the same time, our position within the Milky Way galaxy profoundly affects how we observe and understand celestial phenomena. Our galaxy is part of a small localized group of galaxies known as the Local Group, which contains a few dozen galaxies, including the Milky Way, Andromeda, and several smaller galaxies. This cluster of galaxies is relatively close by in cosmic terms, situated around 22,000 light-years from the galactic center. The Milky Way itself is a spiral galaxy, with its structure defined by swirling arms of stars, gas, and dust. Being located within this spiral galaxy offers both advantages and challenges to astronomers. On the one hand, our position allows us to observe the Milky Way from within, providing a unique vantage point to study its rich structure. The spiral arms are filled with stars, gas clouds, and dust, giving us a clear view of the galaxy's makeup. On the other hand, our position inside the galaxy also means that our view of distant cosmic events is often obscured. Interstellar dust clouds can block the light coming from stars and galaxies beyond, hindering our ability to observe them clearly, especially in certain wavelengths like visible light. To overcome this challenge, astronomers have turned to other forms of electromagnetic radiation, such as infrared and radio waves. These wavelengths have the ability to pass through the dust, allowing astronomers to observe distant stars, galaxies, and other cosmic phenomena that would otherwise remain hidden. This innovative approach is not only essential for understanding the intricacies of our own galaxy, but also for gaining a deeper understanding of the broader universe. As technology advances, astronomers continue to develop new methods to peer through the cosmic dust and unlock the secrets of the universe that lie beyond our immediate view. Through the combined efforts of cutting-edge technology and ongoing research, we are beginning to peel back the layers of mystery that have long shrouded the universe's past. Each discovery brings us closer to understanding the cosmic forces that have shaped our galaxy, our solar system, and ultimately, life itself. The universe's story is still unfolding, and as we continue to explore its depths, we are constantly reminded that the more we learn, the more we realize how much there is still to uncover. Our galactic neighborhood plays a pivotal role in shaping our understanding of the universe, particularly in regard to the enigmatic nature of dark matter. Dark matter, believed to constitute a significant portion of the cosmos's total mass, interacts with the universe solely through gravity, remaining invisible and elusive to direct detection. Yet the challenges posed by observational limitations and the gravitational effects of nearby galaxies like the Andromeda Galaxy often complicate our ability to accurately model its distribution. The gravitational pull exerted by these colossal celestial objects can bend light coming from galaxies that lie much farther away. This phenomenon, known as gravitational lensing, allows astronomers to infer the presence of dark matter, even though it cannot be directly observed. While our position within the Milky Way presents specific hurdles in our observations, it also offers crucial insights that help us unravel the intricate dynamics and history of the universe. As our observational tools improve, the data we gather from our galactic surroundings becomes a vital piece of the cosmic puzzle. It helps us map out the universe's evolution, providing new revelations and perspectives that continuously challenge and expand our understanding. Advancements in technology and novel techniques are allowing astronomers to peer deeper into the cosmos, unveiling discoveries that alter the way we perceive the vast, complex universe. These new breakthroughs are often unexpected, profoundly shifting long-held theories and offering fresh insights into the workings of the cosmos. One such groundbreaking discovery is the detection of gravitational waves, the ripples in spacetime caused by the acceleration of massive objects like colliding black holes or neutron stars. The first detection of these waves in 2016 was a historic confirmation of a prediction made by Albert Einstein over a century ago. This ability to hear these waves opened an entirely new field of astronomy, enabling scientists to observe phenomena previously invisible to traditional telescopes. The study of gravitational waves is revolutionizing our understanding of cosmic events, offering a deeper view into the universe's most extreme and violent occurrences. Another significant breakthrough has been the discovery of fast radio bursts, FRBs, high-energy astrophysical phenomena that release intense bursts of radio waves over incredibly brief periods. The first detection of an FRB in 2007 puzzled scientists as their origins remained mysterious for years. While some FRBs have been linked to distant galaxies and suggest exotic processes such as magnetar activity, their exact source remains an active area of research. This ongoing investigation is pushing the boundaries of our knowledge, opening new avenues for understanding the fundamental mechanisms that govern the cosmos. Similarly, the discovery of exoplanets has radically transformed our understanding of planetary systems. Since the launch of the Kepler Space Telescope in 2009, thousands of planets beyond our solar system have been identified, many of which reside in the habitable zones of their respective stars. These worlds are not only challenging existing theories on planetary formation, but are also sparking the tantalizing possibility of life beyond Earth. As we continue to discover more about these distant planets, the age-old questions about Earth's uniqueness and the potential for life elsewhere in the universe remain a captivating source of scientific inquiry and wonder. Perhaps one of the most profound and transformative concepts in modern cosmology is the discovery of dark matter and dark energy. Despite making up around 95% of the universe's total mass energy content, both of these phenomena remain largely elusive and poorly understood. Among the most remarkable revelations in recent years has been the discovery of the accelerating expansion of the universe driven by dark energy. This finding has forced a reevaluation of fundamental cosmological theories, especially those related to gravity and the universe's eventual fate. These revelations are not only enriching our scientific knowledge, but also suggesting that vast realms of the universe remain beyond our grasp, awaiting further exploration. At the forefront of these scientific breakthroughs is the emergence of artificial intelligence, AI, which has radically transformed the landscape of astronomical research. Modern telescopes generate enormous volumes of data, often amounting to petabytes, far exceeding the capacity of traditional data analysis methods. AI has proven indispensable in handling this massive influx of information. By using sophisticated algorithms, AI can sift through colossal datasets, extracting meaningful patterns and insights that might otherwise go unnoticed. This automation allows astronomers to focus more on interpretation and discovery, rather than becoming bogged down by the sheer scale of raw data. AI is also revolutionizing the identification of celestial objects such as exoplanets, asteroids, and even elusive phenomena like gravitational waves. Machine learning techniques are being applied to analyze light curves, graphs that depict the brightness of a celestial object over time. This is especially useful for studying transitory events such as supernovae or the dimming of stars when a planet transits in front of them. With the help of AI, astronomers can now detect and confirm new celestial objects with remarkable efficiency, accelerating the pace of discovery and deepening our understanding of the universe. The fusion of AI with astronomy is not merely an enhancement, it is fundamentally changing the way we explore the cosmos, unlocking new realms of knowledge at an unprecedented rate. AI has become a transformative force in the field of astrophysics, significantly enhancing the way we predict, simulate, and analyze celestial events. By harnessing its computational power, AI aids researchers in simulating complex cosmic phenomena, helping them predict how galaxies interact, how black holes influence their surroundings, and how stars evolve under various conditions. These simulations offer an unprecedented opportunity to visualize processes that unfold over vast stretches of time, timescales that would be impossible to capture with traditional methods. For instance, scientists can now simulate the collision of galaxies or explore the subtle ways in which black holes warp the space-time around them. These simulations are not just theoretical. They help astronomers gain clearer insights into the mechanisms governing the evolution of the universe. Through this marriage of human intuition and artificial intelligence, novel approaches to cosmological research have emerged. Researchers are now collaborating with intelligent systems capable of suggesting new research directions or pinpointing anomalies in complex datasets that might otherwise go unnoticed. This partnership is fundamentally reshaping not only the tools and methodologies used in astrophysics, but also the very questions that astronomers ask. As a result, it is pushing the boundaries of human understanding, unlocking new discoveries, and offering deeper insights into the cosmos. One of the most remarkable milestones in astrophysics has been the recent breakthrough in our understanding of black holes. These cosmic giants, long shrouded in mystery, have been the focus of intense research, especially after the groundbreaking detection of gravitational waves in 2016. When two black holes collided, they sent ripples through space-time, ripples that were detected by an international network of observatories. This discovery provided direct evidence for a phenomenon predicted by Albert Einstein's general theory of relativity, validating a key aspect of his 100-year-old theory. Not only did this discovery allow us to hear the cosmic symphony produced by black holes, but it also opened up new ways of studying these enigmatic objects, offering a glimpse into their behavior that was previously beyond reach. Then came another pivotal moment in 2019, when the Event Horizon Telescope, a global collaboration of radio observatories, unveiled the first ever image of a black hole's event horizon, often referred to as the shadow of a black hole. This image, which depicted the supermassive black hole at the center of the galaxy M87, was a monumental achievement in modern astronomy. It marked the first time we could directly observe the point of no return around a black hole. The image not only confirmed the existence of black holes, but also provided crucial information about their size and the structure of their surrounding accretion disks. It was a major leap forward in our understanding of the extreme gravitational forces at play in these regions of space. In addition to these groundbreaking observational advances, research into Hawking radiation continues to challenge our understanding of black holes. Proposed by the legendary physicist Stephen Hawking, this concept suggests that black holes might not be eternal, but could slowly evaporate over vast periods of time due to the emission of radiation. Although direct experimental evidence for Hawking radiation remains elusive, this theoretical idea has profound implications. It casts doubt on the notion of black holes as immutable objects and raises deep questions about the fate of the information they consume. This has sparked ongoing debates about the nature of information in the universe, contributing to the broader discourse on the fundamental laws of physics. As technology continues to evolve, so too does our ability to study these mysterious cosmic entities. Next-generation space telescopes and advanced simulation techniques are enabling researchers to explore the inner workings of black holes and their interactions with the surrounding space in more detail than ever before. These new tools are not just helping us to unravel the mysteries of black holes, but also providing key insights into the larger scale evolution of the universe. Every new discovery about black holes offers a deeper understanding of the cosmos, helping us to answer the age-old questions about the origins and future of our universe. Beyond black holes, another groundbreaking theory that has reshaped our view of the universe is the concept of cosmic inflation. This idea proposes that the universe underwent a period of rapid expansion in the moments immediately following the Big Bang. Inflation theory offers solutions to several long-standing mysteries, including why the cosmic microwave background radiation is so uniform despite the vast distances separating galaxies. According to inflationary theory, the universe expanded at a superluminal rate, smoothing out any initial irregularities and giving rise to the uniform structure we see today. Inflation also provides an explanation for the origin of the large-scale structures in the universe, such as galaxies and clusters of galaxies. The tiny quantum fluctuations present during the inflationary period were stretched across the cosmos by the rapid expansion, seeding the matter distribution that would eventually lead to the formation of these massive structures. These fluctuations served as the blueprints for the universe's large-scale structure, which formed as gravity caused regions of higher density to clump together over billions of years. Understanding this process of cosmic inflation has been crucial in answering questions about how the universe evolved from an initially homogeneous state to the rich and complex cosmos we observe today. The insights gained from this theory are not only vital for cosmologists seeking to understand the universe's past, but they also provide a window into its future. By studying the intricate processes that govern the universe's earliest moments, scientists are gradually piecing together the full story of the universe's origins, its development, and perhaps even its ultimate fate. Through the combination of AI-powered simulations, cutting-edge observational techniques, and groundbreaking theories like inflation, our understanding of the universe is expanding at an unprecedented rate, offering a deeper, more detailed picture of the cosmos that continues to evolve with every new discovery. Furthermore, the inflationary theory offers a vital framework for bridging the gap between two of the most fundamental pillars of modern physics, quantum mechanics and general relativity. This intersection is crucial as it paves the way for a more unified understanding of the universe's laws. By studying the quantum nature of the fluctuations that triggered cosmic inflation, scientists are not only examining the early moments of the universe, but are also opening pathways toward unified theories that could merge these two seemingly incompatible areas of physics. These connections go beyond theoretical curiosity. They could lead to groundbreaking discoveries about the underlying mechanisms that govern the cosmos. The predictions of cosmic inflation have gained significant support through a variety of observational data. One of the most compelling pieces of evidence comes from the cosmic microwave background, CMB, the faint radiation left over from the Big Bang. Instruments like the Wilkinson Microwave Anisotropy Probe, EMAP, and the Planck satellite have provided invaluable data revealing patterns that align closely with inflationary models. As scientists continue to refine our understanding of inflation, they are drawing closer not just to answering the how of the universe's evolution, but the much more profound question of why it exists in the form we observe today. This ongoing exploration into the very fabric of the cosmos deepens our appreciation for the delicate balance that governs the vast and complex universe around us. The first ever image of a black hole, captured by the Event Horizon Telescope, EHT, in 2019, marked a monumental achievement in astrophysics, propelling our understanding of the universe into new and exciting realms. This groundbreaking image revealed the supermassive black hole at the center of the galaxy M87, showcasing a glowing ring of hot gas swirling around a dark, seemingly empty region, an image that had previously existed only in the realm of theoretical physics. Yet what made this moment truly significant wasn't just the striking visual. It was the data itself, derived from an innovative collaboration between radio telescopes spread across the globe. This international effort represented a giant leap in our ability to observe celestial phenomena that had once been considered beyond reach. The implications of this image were profound. It provided irrefutable, real-time evidence of black holes' existence, challenging researchers to reassess our understanding of gravity and general relativity. Despite decades of theoretical research and computer simulations, seeing a black hole up close forced scientists to confront the limits of our knowledge about these mysterious objects. In turn, it opened new questions and avenues for research, suggesting that certain aspects of black hole physics remain deeply shrouded in mystery. The image from the Event Horizon Telescope highlighted not only the successes of current scientific endeavors, but also the boundaries that remain to be pushed. What made this achievement even more remarkable was the unprecedented technology and innovative techniques that were required to capture and interpret the data. The image was a product of years of hard work and cutting-edge advancements, proving how concerted global efforts can lead to discoveries that extend the limits of human knowledge. This monumental feat serves as a powerful reminder of the ongoing nature of scientific inquiry, a pursuit that is ever evolving and filled with infinite possibilities for discovery. Each breakthrough in our understanding of the cosmos unveils new questions, suggesting that our journey toward comprehending the universe is far from over. In a broader context, the first image of a black hole underscores the complexities of the universe and the necessity of interdisciplinary collaboration. It reminds us that as we continue to advance our understanding of cosmic phenomena, we are likely to uncover even more profound mysteries, waiting to be unraveled. Each new discovery deepens our sense of wonder and reinforces the idea that the universe is far more intricate and enigmatic than we have yet realized. This constant pursuit of knowledge fuels the quest for understanding that propels scientific discovery forward. In recent years, remarkable progress in the field of astronomy has radically altered our understanding of how planets form. One of the most striking revelations comes from the study of exoplanets, planets orbiting stars beyond our own solar system. Observations have shown that planetary systems often possess configurations that defy previous expectations. For instance, some systems include gas giants that orbit their stars at remarkably close distances, a discovery that directly contradicts earlier theories, suggesting that such massive planets could only form at much greater separations from their stars. This finding challenges long-standing models of planetary formation and forces scientists to reconsider the processes that govern the birth of planets. Another fascinating breakthrough concerns the process by which planets form. Traditional models have suggested that planets grow gradually through the accumulation of dust and gas within a protoplanetary disk. However, recent observations of young star systems reveal that in some cases, planets may form much more rapidly, gathering large amounts of material in brief periods. This has led scientists to consider the role of gravitational instabilities in planet formation, suggesting that massive fragments of the protoplanetary disk could collapse directly into planets within thousands of years back, rather than the millions of years traditionally thought to be necessary. This new understanding of planetary formation has also raised important questions about the diversity of planets observed across the universe. For example, some rocky exoplanets have been found to possess atmospheres rich in gases typically associated with gas giants, such as hydrogen and helium. This finding suggests that planetary formation may occur under a wider range of conditions than previously believed, and that the migration of planets, where planets move from their original positions, may play a significant role in shaping the final architecture of planetary systems. As these discoveries continue to unfold, they reshape not only our understanding of how planets form, but also the diversity of planetary systems that exist throughout the cosmos. These findings underscore the complexity of planetary formation, prompting scientists to revise existing models and delve deeper into the intricate processes at play. As our research continues in this dynamic field, our appreciation for the diverse and evolving nature of planetary systems grows, offering new insights into the cosmic evolution that continues to shape the universe. Advances in spectroscopy, the study of light's interaction with matter, have also revolutionized our ability to analyze the chemical composition of distant exoplanets. By studying the light emitted or absorbed by the atmospheres of exoplanets, scientists can now identify the unique chemical signatures of elements and molecules present on these distant worlds. One of the most important breakthroughs in this area has been the development of specialized telescopes equipped with high-resolution spectrographs. These instruments allow researchers to detect the tiniest changes in light caused by the presence of an exoplanet's atmosphere, revealing gases such as water vapor, carbon dioxide, and even methane. For example, the discovery of water vapor in the atmosphere of an exoplanet located light years away has significant implications for the search for life beyond Earth. It suggests that conditions on some exoplanets may be suitable for supporting life as we know it, sparking widespread excitement about the possibilities of extraterrestrial life. These advancements in spectroscopy are opening up new avenues for exploration, allowing scientists to probe the atmospheres of distant worlds with unprecedented precision, and bringing us one step closer to understanding whether life could exist elsewhere in the universe. With each new discovery, the universe becomes a little more familiar, yet infinitely more mysterious. The more we learn, the more questions arise, driving humanity's insatiable quest to uncover the truths that lie beyond the stars. Advances in technology have revolutionized the way astronomers explore the cosmos, enabling them to detect and analyze fainter signals than ever before, particularly those coming from exoplanet atmospheres. The application of various forms of spectroscopy, such as transmission spectroscopy and secondary eclipse spectroscopy, has opened up new avenues for understanding the complex makeup of these distant worlds. Each technique provides a unique perspective, adding layers of detail to our knowledge by examining how light interacts with different gases at various stages of an exoplanet's orbit. These sophisticated methods not only offer a detailed view of individual exoplanets, but also play a key role in enhancing broader theories about the formation of planets and the diversity of planetary systems across the galaxy. Through the study of the chemical diversity in exoplanet atmospheres, astronomers are uncovering valuable clues about the processes that led to the creation of these distant planets. This research reveals just how diverse the universe truly is, showcasing a stunning variety of planetary compositions and atmospheric conditions that challenge our preconceptions and deepen our understanding of how planetary systems evolve. The growing body of data on exoplanets and their atmospheres suggests that the universe might harbor far more variety than we ever imagined, with planetary systems vastly differing from one another, often in ways we hadn't yet conceived. Gravitational wave astronomy, another remarkable leap in modern science, has drastically transformed our comprehension of the universe. The first direct detection of gravitational waves in 2015 marked a groundbreaking moment in astrophysics, with the subsequent observation of merging black holes becoming one of the most significant revelations in recent years. These waves, produced by the collision of two black holes, not only confirmed the existence of these enigmatic objects in far greater numbers than previously thought, but also provided new insights into the life cycle of stars and the evolution of galaxies. The detection of gravitational waves has proven to be a powerful tool, shedding light on phenomena that were once invisible to traditional telescopic methods. In 2017, another milestone was achieved when gravitational waves were detected from the collision of neutron stars, an event that was not only recorded in gravitational waves, but also in electromagnetic signals across the entire spectrum, from gamma rays to radio waves. This multifaceted observation, known as multi-messenger astronomy, represented the first time the scientific community could study an astronomical event through multiple channels. It provided crucial insights into the formation of heavy elements like gold and platinum, offering a deeper understanding of the processes that forge these precious metals in the universe. These groundbreaking discoveries also have profound implications for our understanding of fundamental physics. The observations of gravitational waves have validated key predictions made by Albert Einstein's general theory of relativity, confirming its accuracy under extreme conditions. Yet, they have also introduced intriguing new questions about the nature of black holes. For example, the discovery of black holes much larger than what was previously believed possible suggests that there are still many mysteries surrounding their formation, structure, and behavior. As research continues, scientists are developing even more advanced gravitational wave detectors to explore phenomena that were once beyond our reach, such as the mergers of supermassive black holes and primordial black holes formed in the early universe. Each new discovery pushes the boundaries of what we know and offers the promise of deeper insights into the fundamental forces that govern the cosmos. The identification of previously unknown celestial bodies has also had a profound impact on our understanding of the solar system, challenging long-held views about its structure and composition. For centuries, we viewed the solar system through a relatively narrow lens, focusing primarily on the 8 officially recognized planets. However, the discovery of dwarf planets such as Pluto, Haumea, and Eris has prompted a reevaluation of what constitutes a planet, leading to a more nuanced and complex understanding of our cosmic neighborhood. These discoveries have also spurred scientists to investigate a vast and largely unexplored region beyond Neptune's orbit, the Kuiper Belt. This expansive zone is home to countless small, icy bodies, further suggesting that the solar system is far more crowded and dynamic than previously thought. The existence of the Kuiper Belt not only adds complexity to our solar system's structure, but it also provides crucial evidence about its origins. The presence of so many small, icy bodies in this distant region suggests that the solar system was once formed from a much larger disk of material, one that continues to exert influence over its evolution today. This expanding knowledge reshapes our understanding of the solar system's formation, highlighting the intricate processes that have shaped its current configuration and continue to affect its evolution. In the grander scheme, these discoveries underscore the idea that our understanding of the cosmos is far from complete. With each new observation, astronomers and physicists push the boundaries of human knowledge, uncovering new mysteries while confirming long-held theories. The universe is vast, complex, and full of surprises, and the more we explore, the more we realize how much there is yet to learn. Whether through the study of exoplanets, gravitational waves, or the hidden corners of our own solar system, we are only just beginning to understand the full extent of the cosmic forces at play. Moreover, the recent detection of fascinating objects such as Oumuamua and Comet Borisov has dramatically expanded our understanding of the cosmos, inviting a new category of exploration: interstellar visitors. These celestial objects are not native to our solar system. They've traveled vast distances from other parts of the Milky Way. Yet, their arrival here provides us with unprecedented opportunities to study materials and processes that might exist far beyond our solar neighborhood. With their erratic, unpredictable trajectories and peculiar characteristics, these objects challenge our preconceived notions of what constitutes a typical space body. The very nature of Oumuamua and Borisov has sparked a flurry of debate. How did they form? What mechanisms might be at play in their origin? And could they hold secrets that impact the evolution of planetary systems? As astronomers and scientists continue to discover similar objects, it forces us to rethink our definitions and classifications of what exists within our solar system. These enigmatic visitors open the door to new realms of scientific inquiry, encouraging a deeper investigation of the nature of celestial objects in general. This constant unveiling of our solar system's secrets serves as a reminder of the enormous vastness and complexity of our cosmic home. It pushes the boundaries of our knowledge and fosters an insatiable curiosity about the universe. The journey of discovery is unending, and with each new revelation, we inch closer to understanding the intricate workings of the cosmos. Simultaneously, private space exploration companies are playing an increasingly vital role in shaping the future of cosmic discovery. Fueled by innovation, competition, and a vision to expand humanity's reach into space, these private entities have introduced cutting-edge technologies while also reducing the prohibitive costs that once made space travel the exclusive domain of government agencies. Their efforts have, in many ways, democratized access to space, paving the way for scientific ventures that were once unthinkable. In particular, the speed at which these companies can develop, test, and launch missions is one of their key advantages. Unlike traditional governmental agencies, private firms often operate with far greater agility, allowing for rapid experimentation and, where necessary, swift adaptation to unforeseen challenges. The success of reusable rockets is a prime example of how the private sector is leading technological advancements that enhance both the efficiency and cost-effectiveness of space missions. The potential for quick, responsive missions, ranging from satellite deployments to manned spaceflights and even ambitious journeys to the Moon or Mars, is a game changer. But perhaps most noteworthy is the growing collaboration between private companies and governmental space agencies. NASA, for example, has increasingly turned to private firms to help achieve its objectives, such as transporting astronauts to the International Space Station. By leveraging the expertise and creativity of these private enterprises, traditional space agencies are free to focus their resources on more ambitious long-term goals, the exploration of distant planets, or even the potential for human settlement on Mars. This collaboration between the private and public sectors is a powerful synergy, combining the strengths of both to further our cosmic ambitions. Moreover, as commercial space tourism gains momentum, the general public's engagement with space exploration is reaching new heights. Ordinary citizens, once excluded from the cosmic frontier, now have the chance to experience space firsthand. This democratization of space access is sparking a renewed interest in the broader implications of space exploration, igniting discussions about the significance of exploring the universe and its relevance to humanity's future. With each mission launched, the narrative surrounding who can venture into space evolves, and the horizons of discovery expand, offering fresh inspiration for generations to come. At the same time, new theories in physics have the potential to radically alter our understanding of the universe, challenging even the most established frameworks. Currently, much of our knowledge of cosmic phenomena is grounded in the principles of general relativity and quantum mechanics. Yet, emerging ideas, such as attempts to unify gravity with quantum physics, promise to offer new ways of thinking about everything from black holes to the very origins of the cosmos itself. For example, theories suggesting the existence of extra dimensions or proposing models like loop quantum gravity could reveal that our universe is part of a much more complex structure than we currently understand. These ideas could provide the key to solving long-standing mysteries such as the nature of dark matter and dark energy, two elusive components that make up roughly 95% of the universe but remain invisible to direct observation. The implications of these new theories are vast. As our understanding of fundamental physics evolves, so too does the potential for groundbreaking discoveries that may reshape our entire conception of cosmic evolution. With the advent of next-generation telescopes capable of peering deeper into space, we could soon gather evidence that either supports or refutes these bold ideas. This could offer new insights into phenomena such as the accelerating expansion of the universe or the conditions present during the Big Bang. Such advancements could redefine the timeline of the universe's history, giving us a clearer, more complete picture of cosmic evolution. Beyond the academic sphere, these theoretical advancements may have far-reaching practical applications. A deeper understanding of the laws of nature could lead to breakthroughs in technology, shift philosophical perspectives, and even provide new frameworks for approaching fundamental questions about the nature of existence itself. As scientists continue to push the boundaries of knowledge, our comprehension of the universe will undoubtedly evolve in profound and unexpected ways. The next few decades hold the promise of uncovering truths that have, until now, remained beyond our grasp. Meanwhile, the prospect of colonizing other planets within our solar system represents another exciting frontier. Establishing a human presence on worlds like Mars or the moons of Jupiter offers the opportunity not only to extend the reach of humanity, but also to unlock a wealth of scientific knowledge. For instance, by studying how human biology adapts to environments vastly different from Earth, such as the harsh, arid conditions on Mars or the icy, low-gravity surfaces of Europa, scientists could uncover crucial insights into human health, potentially leading to new medical treatments. Moreover, the exploration of these extreme environments may provide clues to the broader question of life's origins and its potential existence beyond Earth. Understanding how life could survive or even thrive in such hostile conditions might inform the search for extraterrestrial life, giving us a better understanding of the factors necessary for life to emerge elsewhere in the universe. The unfolding story of space exploration is not merely a tale of technological progress. It is a journey into the very heart of our curiosity about the cosmos. And as we continue to push the boundaries of what is possible, we may yet uncover answers to some of humanity's most profound questions, forever changing our understanding of the universe we call home. Colonization efforts have the potential to not only reshape our future, but to also accelerate advancements in technology. As humanity looks toward living on other planets, the unique challenges of extraterrestrial environments push the limits of what we can achieve. The development of life support systems, sustainable energy solutions, and radiation protection technologies will be at the forefront of these efforts. The same innovations that are designed to make life possible on Mars or the Moon could in turn be applied to address critical problems here on Earth, such as the energy crisis or climate change. These breakthroughs may pave the way for new technologies that could revolutionize industries and improve global living conditions, fostering an entirely new era of innovation. Moreover, colonizing other planets would significantly enhance our understanding of the forces that shape planetary processes. By conducting geological studies on otherworldly surfaces, such as the Martian terrain or the subsurface oceans of Europa, scientists can uncover vital information about the history and evolution of our solar system. These investigations would not only shed light on the potential for life elsewhere, but also help us understand how our own planet came to be, offering a broader and deeper context for studying Earth itself. It would be a crucial step in piecing together the cosmic puzzle that spans billions of years. The pursuit of life beyond Earth holds another profound benefit. It could inspire a new generation of scientists, engineers, and thinkers. As we set our sights on ambitious goals for planetary colonization, the collective pursuit encourages collaboration across borders, driving investment in science, technology, engineering, and mathematics, STEM education. The excitement and wonder surrounding space exploration could unite humanity in a shared mission, fostering global responsibility for the future of our planet. The challenge of exploring the unknown sparks the imagination and reinforces the idea that together we are capable of achieving the extraordinary. In tandem with the pursuit of colonization, the study of space-time, the fabric that links space and time together, plays a pivotal role in our understanding of the universe. Space-time not only describes the position of objects within the cosmos, but also how they move and interact over time. This framework allows scientists to make predictions about cosmic phenomena such as the expansion of the universe, the behavior of gravity, and the formation of galaxies. One of the key contributions of space-time theory is its portrayal of gravity as a distortion or curvature in the fabric of space itself. Massive objects like stars and planets create ripples or waves in space-time, which influence the movement of nearby celestial bodies. These interactions allow us to predict the trajectory of galaxies and to understand the larger structure of the universe, providing us with a more complete picture of the cosmos. Through space-time, we can also study the fate of the universe. Current observations show that the universe is expanding at an accelerating rate, propelled by a mysterious force known as dark energy. By tracking the movement of galaxies and applying the equations of general relativity, scientists are able to formulate hypotheses about the long-term future of the universe. Will it continue expanding forever? Could it eventually collapse? Or might it settle into a stable state? The answers to these questions are still unknown, but studying space-time is crucial for understanding what lies ahead. The knowledge gleaned from these investigations could reveal the evolution of the universe, from the first moments after the Big Bang to the far distant future, possibly billions of years from now. The implications of space-time studies are staggering, as they provide insight into the relationship between dark matter, dark energy, and the very fabric of the universe. These elements may hold the key to understanding cosmic evolution, including the origins of galaxies and the fate of the universe in the far-off future. Investigating the interplay between these forces could shed light on everything from the early moments of the Big Bang to the eventual heat death of the universe, a theory that suggests the universe may eventually reach a state of maximum entropy. In other words, exploring space-time offers us a unique window into the universe's past, present, and future. Looking to the next 50 years, technological advancements will play a crucial role in shaping the future of space exploration. One area of major focus is propulsion technology, which is poised for a revolutionary transformation. Traditional chemical rockets may soon be supplanted by more efficient propulsion systems, such as ion and nuclear thermal propulsion. These methods could drastically reduce travel time, making it feasible to explore distant destinations like Mars, or even venture further into the outer reaches of the solar system. More efficient travel will open up new possibilities for human exploration and settlement on other planets, while also creating a foundation for deeper scientific investigations. In parallel with advancements in propulsion, robotics, and artificial intelligence, AI will redefine how we explore the cosmos. Imagine space probes equipped with cutting-edge AI systems capable of executing autonomous missions on distant planets and moons. These robots could conduct scientific experiments, gather data, and even build structures in space, all without human intervention. As AI continues to evolve, these robots will become more adaptable, able to respond to unforeseen challenges and conditions. This makes them indispensable for missions where human presence is limited or impossible, such as long-duration expeditions to the outer planets or beyond. The advancements in space exploration technology, propulsion, robotics, and AI hold the promise of transforming how we interact with the universe. As we push the boundaries of what is possible, we open new doors to discovery and understanding, enriching our knowledge of the cosmos and creating a future where the stars may no longer be out of reach. In the coming years, the concept of reusable spacecraft is poised to become the standard rather than the exception. Major space agencies and private companies around the world are already developing cutting-edge technologies that enable the safe landing and refurbishment of rockets. This innovation could dramatically slash the costs associated with space travel, making space exploration a much more feasible endeavor for organizations of all kinds. The more affordable access to space becomes, the more frequent and diverse our missions are expected to be, expanding humanity's reach into the cosmos. As this new era of space exploration unfolds, advancements in life support systems and habitat technologies will be critical for the success of long-duration missions. Innovations that allow for the recycling of air and water, as well as growing food in space, will be essential in supporting human crews on extended journeys, particularly missions to Mars and beyond. These developments will enable sustained human life in environments far removed from Earth, paving the way for humanity's next great leap into the unknown. As technology improves, the dream of sustainable living in space will no longer be a distant vision, but a tangible reality. However, the future of space exploration is not only shaped by technological advancements, it is also heavily influenced by a new wave of responsibility toward ensuring that our cosmic endeavors are both sustainable and ethical. As humanity gazes upward, space agencies and private companies alike are increasingly focused on minimizing our environmental impact, not just on Earth, but beyond it. This effort to safeguard our planet's legacy while exploring new worlds is reflected in a growing commitment to efficient resource use and waste reduction. Fuel efficiency and advanced propulsion systems, for example, are being developed to reduce the number of launches needed and to lessen the fuel consumption of spacecraft during their missions. Another pivotal aspect of responsible space exploration is the preservation of extraterrestrial environments. Legislation such as the Outer Space Treaty, established in the 1960s, encourages nations to avoid harmful contamination of space bodies, and this principle has only grown in importance. As we plan missions to the Moon, Mars, and beyond, stringent measures will be taken to ensure that we do not introduce Earth's microbes into foreign ecosystems, where they could disrupt delicate balances. These planetary protection protocols are critical for maintaining the integrity of the environments we aim to explore, allowing us to conduct our missions ethically and scientifically. In parallel, the utilization of local resources, what is known as in situ resource utilization, has the potential to revolutionize the way we approach space exploration. This technology allows astronauts to extract resources directly from other planets, reducing the need to transport every item from Earth. For example, extracting water from the lunar surface to produce hydrogen fuel could significantly reduce the logistical burden of missions while also supporting sustainable human presence on the Moon and beyond. This approach could transform planets like Mars from mere destinations into hubs for further exploration and even human habitation. As we venture deeper into the cosmos, collaboration will be essential. Education and international cooperation are critical components of responsible space exploration, as fostering a global dialogue on the ethical and scientific implications of our actions can guide our collective progress. By encouraging collaboration among scientists, policymakers, and the public, we can promote shared values and work together toward the future of space exploration. The commitment to sustainability, efficiency, and planetary protection will not only ensure that humanity's ventures into space are responsible, but will also leave a lasting legacy for future generations. As humanity sets its sights on the future, several groundbreaking missions are already on the horizon, each poised to unlock new secrets about our universe. One of the most eagerly anticipated missions is the James Webb Space Telescope, which will offer unprecedented clarity as it peers deep into the cosmos. This powerful telescope, capable of observing infrared light, will allow us to look back in time and witness the formation of stars and galaxies, as well as study planetary systems and even the atmospheres of exoplanets. Its ability to see through dust clouds that typically obscure our view promises to reveal crucial details about distant worlds, providing insights that were previously unimaginable. Another monumental mission on the near horizon is the Mars Sample Return mission. This mission aims to bring samples from the Martian surface back to Earth, where they will be analyzed in detail. By studying these samples, scientists hope to uncover the geological history of Mars and search for signs of ancient life. This mission represents a significant leap forward in our understanding of the Red Planet, offering the potential to reveal much more than robotic rovers alone could ever achieve. Across the Atlantic, the European Space Agency is preparing to launch the Euclid mission, which will focus on unraveling the mysteries of dark energy and dark matter, two of the most enigmatic components of the universe. By mapping the three-dimensional distribution of galaxies and measuring their rate of expansion, Euclid could provide invaluable insights into the forces that govern the cosmos, including how gravity shapes cosmic structure and the ultimate fate of the universe itself. These missions are not just about expanding our geographic reach, they are about challenging and redefining our understanding of fundamental concepts in cosmology. Each new discovery holds the potential to reshape our view of the universe and our place within it. By embarking on these journeys, we are not simply exploring new frontiers, but pushing the boundaries of what we know, enriching our understanding of the physical laws that govern everything around us. In this new age of exploration, quantum computing stands to revolutionize astrophysical research. With its unparalleled computational power, quantum computing has the ability to process vast amounts of data and solve complex problems that are currently beyond the capabilities of traditional supercomputers. While classical supercomputers are incredibly powerful, they still struggle with the scale and complexity of astrophysical simulations. Quantum computers, however, could carry out these simulations at unimaginable speeds, allowing scientists to model complex systems such as the formation of galaxies and the dynamics of black holes. Tasks that would typically take weeks or months to complete could be finished in a matter of hours, allowing for faster iterations and deeper insights. This unprecedented acceleration in computational power could lead to a leap in our understanding of some of the most perplexing cosmic phenomena. With the help of quantum processors, researchers could investigate the mysteries of dark matter and dark energy with a level of precision and efficiency previously thought impossible. The power to unlock these cosmic puzzles could redefine our understanding of the universe itself, as quantum computing opens new doors to discovery that were once beyond our grasp. Quantum computing stands at the frontier of revolutionizing many fields, and one area where its impact could be transformative is in the realm of astrophysics. As astronomers continue to scan the heavens for signs of the universe's hidden mysteries, the volume of data they gather has reached unprecedented scales. Observatories now collect vast troves of information from across the cosmos, creating a monumental task for researchers seeking to find meaningful insights amidst the noise. Here, quantum algorithms could play a pivotal role, providing the computational power necessary to process these enormous datasets more efficiently than ever before. By harnessing the potential of quantum computing, scientists could greatly enhance their data analysis techniques. These quantum-enhanced algorithms have the potential to unravel complex signals such as gravitational waves or the subtle transits of exoplanets, which might otherwise remain undetected by conventional computing methods. As quantum technology continues to evolve, it will likely accelerate discoveries in ways we can only begin to imagine, pushing the boundaries of our current knowledge. This convergence of quantum computing and astrophysical research could yield profound insights into the cosmos. Researchers might soon be able to probe questions that have remained tantalizingly out of reach, illuminating mysteries that have long perplexed humankind. With each breakthrough, the field of space exploration could usher in a new era, one where we not only explore the universe but understand its most profound truths. Yet, as we stretch our reach into the cosmos, we are also faced with a host of ethical questions that must be addressed. The impact of human exploration on other celestial bodies, whether through exploration, resource extraction, or potential colonization, poses complex moral dilemmas. As we look to explore Mars, the icy moons of Jupiter, and beyond, we must consider our responsibilities towards these new frontiers. The concern isn't merely about the contamination of pristine environments. It also extends to the broader implications for any life forms that might already exist or have once called these distant worlds home. One key ethical consideration is planetary protection. If we venture into environments such as Mars or Europa, we risk introducing terrestrial microbes that could potentially disrupt local ecosystems if they exist. This creates a moral quandary. Do we have the right to explore and alter other planets without fully understanding the potential consequences of our actions? The possibility of irreversible changes to native ecosystems, should they exist, raises further questions about stewardship and the preservation of cosmic heritage. Beyond planetary protection, the issue of resource exploitation looms large. As humanity looks toward the mining of asteroids or the colonization of other planets, a philosophical debate emerges. Is it ethical to exploit these celestial bodies for raw materials or human habitation? The specter of space colonization evokes historical parallels with colonialism, where new lands were exploited without regard for the inherent value of the land itself or the long-term consequences of such actions. The ethical complexities deepen further when we consider the right to claim ownership over these barren worlds. Should we, as a species, assert dominion over planets, moons, and asteroids simply because we have the technology to do so? This question challenges our assumptions about ownership and human entitlement on a cosmic scale. Moreover, the social implications of space exploration extend far beyond the confines of outer space. As we push the boundaries of exploration, we must consider how our actions in space reflect the values of our civilization here on Earth. The policies we establish regarding space exploration can either foster international cooperation or exacerbate existing political tensions. Striking a balance between exploration and responsibility may be one of the greatest ethical challenges humanity faces in the coming decades. The goal should be to ensure that the benefits of space exploration are shared by all of humanity and not confined to a privileged few. Human curiosity has always been a driving force behind scientific progress. Our innate desire to understand the world around us has propelled us to explore the unknown. And it is this same curiosity that pushes us to look beyond our home planet and into the vast expanse of space. From the earliest civilizations, which gazed upon the stars and sought to unravel their mysteries, to today's scientists who use cutting-edge technology to probe the furthest reaches of the cosmos, our quest for knowledge has led to monumental breakthroughs in our understanding of the universe. This relentless pursuit of knowledge has led to some of the most fundamental questions in science. Why are we here? How did the universe begin? What lies beyond the stars? Each discovery leads to new questions, creating an unbroken cycle of inquiry that propels us forward. One of the most profound examples of this drive is the quest to understand dark matter and dark energy, two phenomena that together make up the vast majority of the universe's mass and energy content. Despite the fact that they remain elusive, our desire to uncover their secrets drives innovation in both theoretical and experimental physics. Beyond the realm of theoretical questions, our curiosity also leads to tangible technological advancements that have a direct impact on life here on Earth. Satellite technology, for example, enables communication, navigation, and weather prediction, all of which have become indispensable in modern society. Similarly, the exploration of Mars not only aims to answer the age-old question of whether life exists beyond Earth, but also drives innovations in robotics, renewable energy, and sustainable living technologies, advances that can benefit humanity in profound ways. The pursuit of knowledge also fosters a sense of connection between humanity and the cosmos. When we look up at the night sky, we are reminded that we share a common experience with all people throughout history and across cultures. This collective curiosity unites us, drawing together scientists, dreamers, and everyday individuals as we explore the fundamental story of existence. A story that is filled with wonder and mystery. It underscores the importance of continuing our quest for knowledge, as each step forward brings us closer to understanding the universe in ways that can enrich our lives. Storytelling, too, plays an essential role in this quest. As a tool for bridging the gap between complex scientific concepts and public understanding, storytelling allows us to relate to the abstract and sometimes overwhelming ideas of astronomy. By framing these concepts in the form of narratives, storytellers make the unknown more accessible, transforming dry facts into engaging tales that invite curiosity rather than confusion. Ancient cultures, for instance, used myths to explain natural phenomena, and today, modern science continues this tradition by telling the story of the stars, planets, and galaxies. A perfect example of this is the life cycle of a star. Instead of merely listing the scientific stages, nebula, fusion, supernova, or white dwarf, a storyteller might describe it as a journey. The birth of a star from the swirling gases of a nebula, the fiery stage of fusion that powers it, and the eventual death of the star, either in a violent explosion or a quiet fading into the cosmos. This narrative approach not only makes it easier for people to grasp the enormity of the process, but also taps into emotions and familiar experiences, grounding the abstract in relatable terms. Furthermore, storytelling humanizes astronomy. By highlighting the individuals behind the discoveries, their struggles, triumphs, and moments of inspiration, stories make the science more personal. Audiences are not just learning about distant galaxies. They are connecting with the scientists who devoted their lives to uncovering the universe's secrets. This connection fosters a deeper emotional engagement with the subject matter and often sparks a lifelong interest in space exploration. Through this blend of facts and storytelling, audiences are more likely to develop an interest in astronomy, which in turn nurtures a society that is both informed and curious. The more people are exposed to these stories of cosmic exploration, the more they will come to appreciate the importance of science and the profound mysteries of the universe. Cultural interpretations of the cosmos have been intertwined with the evolution of scientific thought for centuries. In ancient times, civilizations looked to the skies not only to understand natural phenomena, but to seek deeper meaning about life itself. For instance, the Babylonians meticulously recorded the movements of celestial bodies, viewing the heavens as a reflection of earthly events and a means of interpreting their world. Their observations laid the foundation for later astronomical work, helping to shape our modern understanding of the cosmos. In ancient Greece, philosophers like Aristotle and Ptolemy developed models of the universe that placed Earth at its center, a view that dominated Western thought for centuries. This geocentric model, however, was not merely based on observations, but was also shaped by cultural and philosophical beliefs about humanity's place in the universe. It wasn't until the Renaissance that the heliocentric model, proposed by Copernicus, began to challenge these long-held assumptions. The Age of Enlightenment further accelerated this shift, as thinkers like Isaac Newton ushered in a mechanistic view of the universe governed by natural laws. Today, cultural influences continue to shape how we interpret the cosmos. Different societies have developed unique creation myths, each offering a distinct perspective on the origins of the universe. Modern theories, such as the multiverse hypothesis, reflect not only scientific advancements, but also the existential questions that humanity faces in the contemporary world. These stories, ancient and modern alike, remind us that our understanding of the cosmos is not just a scientific endeavor, but a deeply human one, shaped by our values, our fears, and our aspirations. As we continue to venture further into the vast expanse of space and contemplate the possibility of life beyond Earth, the interplay between science and culture remains as dynamic as ever. Our collective imagination is continually shaped by the diverse cultural interpretations of the cosmos, each perspective feeding into our scientific endeavors, sparking curiosity and inspiring new inquiries. Popular media plays an integral role in shaping this dialogue, often blurring the lines between scientific fact and speculative fiction, weaving together narratives of cosmic phenomena with the thrill of imaginative storytelling. This rich tapestry of space-related portrayals stretches across documentaries, captivating viewers with real-world scientific explorations and science fiction, igniting the wonder of extraterrestrial encounters and interstellar adventures. These representations, whether grounded in real science or fantastical speculation, fuel a growing sense of curiosity about the universe. They prompt audiences to delve into topics such as black holes, dark matter, and the potential for extraterrestrial life. In doing so, they invite us to ponder our place within the cosmos and to explore the mysteries that lie beyond our home planet. Films like Interstellar, for instance, bring to life complex concepts such as time dilation and the effects of gravity on space travel, drawing viewers into discussions about the fabric of the universe itself. This kind of dramatization plays a vital role in making abstract scientific ideas more accessible to a broad audience, fostering an enthusiasm for astronomy and physics, and encouraging future generations to pursue careers in science, technology, engineering, and mathematics, STEM. However, while these cinematic explorations often open the door to scientific curiosity, they can also lead to oversimplifications, which in turn may distort public understanding. For example, recurring depictions of hostile alien encounters, though thrilling, tend to overshadow the more grounded scientific quest for microbial life on distant planets. These exaggerated portrayals can create misconceptions about the nature of space exploration and the focus of current research. Despite these challenges, the overall impact of popular media on public interest in space remains overwhelmingly positive. By fostering wonder and sparking curiosity, it contributes to an ongoing dialogue about the universe and humanity's role within it, ultimately encouraging support for scientific research and the pursuit of knowledge. As this public interest in the cosmos grows, so too does the involvement of ordinary citizens in the exploration of space. Citizen science, a movement that bridges the gap between professional scientists and the general public, has revolutionized the way we explore and understand the universe. Through initiatives like Galaxy Zoo, where volunteers classify galaxies based on their shapes, and Planetary Resources, which encourages individuals to track near-Earth objects such as asteroids, the public now plays an active role in scientific discovery. These projects invite anyone with an interest in space to contribute to the growing body of astronomical knowledge. Citizen scientists analyze data from telescopes, participate in real-world research, and help make critical contributions that advance our understanding of celestial phenomena. Whether it's classifying stars or monitoring planetary movement, these volunteers are integral to expanding our comprehension of the cosmos. One of the driving forces behind this new era of accessible astronomy is the rapid advancement of technology. Today, digital tools and online platforms allow individuals around the world to access real-time data from some of the most advanced telescopes and space observatories. This accessibility has transformed astronomy from a specialized field reserved for experts into a global, collaborative effort. With just an internet connection, enthusiasts and amateur astronomers can join the ranks of citizen scientists, working side by side with professionals to unlock the secrets of the universe. The psychological effects of contemplating the vastness of space are equally profound. For many, the mere thought of the universe's staggering size, stretching out in every direction, seemingly without end, evokes a deep sense of awe. This sense of wonder often leads to introspection, prompting individuals to reevaluate their place in the grand scheme of existence. The realization that Earth is but a tiny speck in an unimaginably vast universe can stir feelings of connection and unity, not only with fellow humans, but with the very cosmos itself. In moments of reflection, many find solace, recognizing the shared journey of humanity and the interconnectedness of all life. Yet for some, the contemplation of an expansive and indifferent universe may stir anxiety and existential uncertainty. The recognition that the universe continues without regard for human existence can evoke feelings of insignificance and fear. Questions about the meaning of life, the purpose of humanity, and our future in the face of an ever-expanding cosmos may overwhelm those who are left grappling with their place in this boundless space. Interestingly, the psychological impact of space exploration varies widely, depending on an individual's beliefs, values, and worldview. For some, cosmic revelations provide a sense of spiritual fulfillment. integrating the science of the universe into their broader philosophical or religious views. For others, the pursuit of knowledge becomes a source of motivation, encouraging them to explore new scientific frontiers or to contribute to humanity's collective understanding of its origins and future. This sense of purpose, whether spiritual, scientific, or otherwise, can serve as a powerful catalyst for personal growth and resilience in the face of uncertainty. Engaging with the cosmos, whether through scientific inquiry or personal reflection, fosters creativity, intellectual curiosity, and a broader sense of connection with the world around us. The pursuit of knowledge about the universe doesn't merely enrich our understanding of the cosmos, it expands our understanding of ourselves. In this way, the exploration of space becomes a mirror for our own existential questions, challenging us to consider the significance of our shared journey among the stars. The educational impact of this growing fascination with the universe cannot be overstated. When students are captivated by the mysteries of space, their curiosity is ignited, fueling an intrinsic motivation to explore scientific concepts. This sense of wonder leads to deeper engagement with complex topics, from the origins of stars to the potential for life on distant planets. The questions raised by the universe are endless, and this constant stream of inquiry encourages critical thinking and the development of problem-solving skills. By inspiring the next generation to ask questions, seek knowledge, and push the boundaries of understanding, we ensure that the exploration of space will continue to fuel innovation, creativity, and discovery for years to come. A sense of wonder is a powerful catalyst for collaboration and creativity among students. As they dive into scientific investigations and explore technological innovations, the mysteries of the universe unfold before them, prompting not only curiosity but also a strong desire to work together. In this environment, students often find themselves engaging with peers, combining their strengths, and building upon each other's ideas in pursuit of answers. This collaborative atmosphere fosters an exchange of thoughts where communication and teamwork become central to the learning process. Through shared experiences and collective problem-solving, students establish a vibrant community of inquiry. Within this space, ideas flow freely, and the very essence of scientific discovery comes to life, sparking innovations that could change the course of history. The power of wonder doesn't stop at group discussions or team projects. It also bridges the gaps between different academic disciplines. When education is infused with a sense of awe and curiosity, the barriers that separate subjects like science and technology begin to dissolve. Students are encouraged to think beyond the traditional boundaries, realizing that knowledge is not confined to neat, isolated categories. For example, the principles of physics can enhance our understanding of biological systems, while insights from ecology may inspire new technological solutions for environmental conservation. This interdisciplinary approach reflects the interconnectedness of the universe itself, revealing that all areas of knowledge are deeply intertwined. As students explore the overlaps between disciplines, they develop a holistic perspective on the world. This approach equips them to navigate the complexities of our rapidly evolving global society, fostering a sense of responsibility and a readiness to tackle the challenges that await them. Ultimately, wonder transforms education into a grand adventure, one that extends far beyond the confines of textbooks and classrooms. It nurtures the minds of future scientists, engineers, and innovators, but it also shapes informed citizens with a deep appreciation for the world around them. This sense of awe encourages people to not only seek knowledge, but also become active participants in solving the critical issues facing society. By tapping into the innate curiosity of students, we can ensure that the next generation is not only well-educated, but also passionate about creating solutions that address the pressing challenges of the future. Community engagement in fields like astronomy plays a pivotal role in enhancing scientific literacy, making complex concepts more accessible and relatable to the public. Through events such as star parties and planetarium visits, individuals are invited to explore the wonders of the universe firsthand. These activities spark curiosity, prompting people to ask questions and seek answers, thus deepening their understanding of astronomical phenomena and the scientific method itself. Beyond passive observation, community members are also encouraged to actively contribute to scientific research through citizen science projects. By collecting data, analyzing findings, or even making direct observations, individuals become hands-on participants in the scientific process. This active involvement fosters a deeper, more practical understanding of scientific principles while honing critical thinking skills. Furthermore, community astronomy clubs and outreach programs offer tailored educational resources to individuals of all ages and backgrounds. These resources, which may include interactive exhibits, storytelling, and engaging presentations, help bridge the gap for those who may not have access to advanced scientific curricula. By presenting complex ideas in a manner that is both engaging and understandable, educators make science more approachable for everyone, regardless of their prior knowledge. As these discussions unfold, they often lead to broader conversations about pressing global issues, such as climate change and the impact of technology on society. This dialogue not only raises awareness, but also empowers communities to engage meaningfully with scientific issues that have a direct impact on their lives. The cultivation of scientific literacy through community engagement helps individuals develop the tools necessary to navigate the complexities of modern science and technology. When communities gain a deeper understanding of how the world works, from the behavior of natural forces to the role of technology in shaping our future, they become better equipped to make informed decisions and participate in conversations that affect their collective well-being. In this way, community involvement becomes a vital part of the scientific process, enriching both the individual and the collective with knowledge that will shape the future. Among the myriad wonders of the universe, there are certain astronomical phenomena that add an extra layer of mystery, often overlooked by the general public. One such enigma is the magnetar, an incredibly rare type of neutron star with a magnetic field that is 1 billion times stronger than that of an average neutron star. These magnetic fields can emit powerful bursts of energy, occasionally resulting in gamma-ray bursts, the brightest explosions in the cosmos. Despite their immense power and fascinating properties, magnetars remain relatively unknown in popular discussions about space, leaving many questions unanswered about their true nature and their role in the broader universe. Another captivating cosmic mystery is the cosmic microwave background radiation. This faint, pervasive glow fills the universe, acting as a kind of afterglow from the Big Bang itself. It provides scientists with a glimpse into the state of the universe just 380,000 years after its formation. Understanding this relic allows astronomers to gather essential information about the shape and composition of the universe, helping to shape our current theories of cosmic evolution. Interestingly, it also lends support to the theory of cosmic inflation, a rapid expansion of space that occurred just moments after the Big Bang. Yet, despite its profound significance, the cosmic microwave background radiation remains largely invisible to the untrained eye, with many unaware of its crucial role in our understanding of the universe. Another intriguing mystery of the cosmos lies in the existence of rogue planets, celestial bodies that wander through the galaxy without being bound to any star. These planets, which may have originally formed around a star, were ejected due to gravitational interactions. Estimates suggest that there could be more rogue planets in our Milky Way galaxy than there are stars. These solitary planets drifting through space without a fixed point of orbit challenge our understanding of planetary formation and survival. Their existence raises fascinating questions about the conditions under which life could potentially emerge on these wayward worlds, far from the warmth of a star. Each of these phenomena serves as a reminder of the complexity and mystery of the universe, urging us to look beyond the familiar and embrace the unknown. Through education, collaboration, and community engagement, we can continue to unlock the secrets of the cosmos, one discovery at a time. Dark matter, once dismissed as a mere hypothesis, has become one of the most captivating enigmas of modern astrophysics. Although it remains invisible and undetectable by traditional means, scientists believe it constitutes about 25% of the universe. Its presence is inferred by the gravitational effects it has on visible matter and light in the cosmos. Despite its intangible nature, dark matter exerts a profound influence on the behavior of galaxies, galaxy clusters, and the expansion of the universe. The search for a true understanding of dark matter is a quest that continues to elude the scientific community, posing questions that have the potential to redefine our very understanding of the cosmos. Its elusiveness means that it often goes unnoticed in everyday conversations about astronomical phenomena. Yet the mysteries surrounding it, and other phenomena like it, underscore the infinite complexities of the universe, which is filled with enigmas waiting to be unraveled. For millennia, the stars above have not only inspired awe, but have profoundly shaped human civilization. From ancient cultures to modern societies, our understanding of the heavens has influenced everything from religious practices to political power. Celestial bodies were once viewed as much more than distant lights in the night sky. They were imbued with meaning, their movements seen as signs and omens that explained natural occurrences and human emotions. These early myths and stories provided frameworks for understanding the universe, guiding everything from agricultural cycles to navigation, and the creation of calendars. In ancient Egypt, for example, the stars were not just objects of worship, but integral to the very design of their monumental architecture. The pyramids were deliberately aligned with certain stars, and deities linked to celestial phenomena were honored in temples and rituals. The Mayan civilization, similarly, placed great importance on the heavens, crafting an incredibly sophisticated calendar system that was crucial not only for predicting astronomical events, but also for determining the right times for planting and harvesting crops, as well as for religious ceremonies. These intricate systems showed how intertwined astronomy was with daily life, influencing social structures and even the rhythm of the seasons. Moreover, the constellations served not only as markers for navigation, but as rich tapestries of cultural stories and values. For many ancient societies, the patterns in the sky told stories of gods, heroes, and the fundamental lessons of life. In Greece, the stars gave rise to philosophical musings, prompting early scientific investigations into the nature of existence and the cosmos. For indigenous cultures around the world, the night sky often played a vital role in the creation myths that shaped their collective identity. These myths weren't just stories, they were blueprints for understanding the world and our place within it. Over time, the stars have influenced far more than the myths and spiritual practices of ancient peoples. The movements of celestial bodies were often seen as harbingers of political change, with astrological predictions offering counsel to rulers and leaders. In this way, the heavens had a hand in shaping the destiny of nations, guiding decisions that affected not just individuals, but entire civilizations. Celestial phenomena marked the passage of time, signaling seasons of war, peace, or prosperity. In this sense, the stars were more than passive observers. They were active participants in the unfolding drama of human history, a reminder of the deep connection between humanity and the cosmos. Professional astronomers, tasked with studying these celestial phenomena, often live lives that are far from ordinary. Their work requires a unique set of habits, many of which revolve around the peculiar hours required for observing the night sky. The Earth's atmosphere tends to be more stable and calm during the night, providing clearer views of distant stars and galaxies. As a result, astronomers often work late into the night, adjusting their sleep schedules to maintain peak focus and productivity. This nocturnal lifestyle, though necessary for the pursuit of knowledge, can make their daily lives feel out of sync with the rest of society. Because their research often involves long, solitary periods, whether spent in remote observatories or in front of data screens, astronomers develop ways to cope with the isolation. Many turn to hobbies such as photography, capturing both the beauty of the night sky and the intricate details that their telescopes reveal. Others immerse themselves in the world of technology, developing new software tools or honing their programming skills to enhance their ability to analyze and interpret vast amounts of astronomical data. Despite the solitary nature of their work, astronomers often rely on collaboration and community engagement to stay connected with the larger scientific world. They attend conferences, participate in online forums, and engage with the public through outreach initiatives, sharing their discoveries and fostering a sense of camaraderie within the scientific community. This intellectual journey is not solely about uncovering the secrets of the universe. Astronomers are often voracious readers. delving into fields as diverse as philosophy, history, and the arts. By exploring these areas, they can place their scientific findings within a broader context, enriching their understanding and offering fresh perspectives on their research. The pursuit of knowledge for many astronomers becomes a lifelong journey of continuous learning, a process that blends empirical data with abstract ideas and creative expression. The connection between science and art is not always obvious, but it is profound. Just as astronomers seek to understand the universe through data and observation, artists attempt to capture the vastness and complexity of the cosmos through their own medium. The discoveries of astronomers, whether a new galaxy, a black hole, or a supernova, become a rich source of inspiration for artistic expression. These cosmic revelations provide artists with the raw material to explore themes like existence, time, and the infinite. Through painting, sculpture, and other forms of creative expression, artists transform abstract scientific concepts into visual narratives that evoke emotion and provoke thought. The grandeur of the night sky, the intricate patterns of galaxies, and the delicate dance of planets and stars are depicted in ways that make the unimaginable tangible. Art and science thus converge in a shared desire to comprehend the universe. Through their respective lenses, both astronomers and artists try to make sense of the cosmos, one through reason and observation, the other through emotion and creativity. This intersection of disciplines fosters a deeper public understanding of both the scientific and artistic worlds. In doing so, it not only enriches our cultural heritage, but also brings us closer to understanding the mysteries of the universe. As technology advances, new tools are opening up a world of possibilities for artists, enabling them to integrate scientific data directly into their creative expressions. Today, a growing number of contemporary artists are exploring the universe through astronomical imagery and data sets, transforming the abstract, numerical language of science into visually striking works of art. This fusion of art and science fosters a unique dialogue about perception, knowledge, and the mysteries that stretch far beyond our immediate grasp of reality. In many ways, these collaborations reveal how art and science are united in their shared mission to explore the unknown. Art's relationship with science is not limited to inspiration or interpretation. It extends into meaningful partnerships between artists and scientists aimed at creating educational tools. These collaborations help bridge the often vast gap between complex scientific concepts and the general public, making the vastness of the cosmos more accessible. Through the lens of art, we are better able to engage with difficult scientific ideas, and in turn, this cross-disciplinary work ignites further creativity. It cultivates a rich tapestry where science and art are not merely juxtaposed, but work in harmony, shaping our understanding of the universe and inspiring future generations. Unexpected discoveries in the field of astronomy have dramatically reshaped our understanding of the cosmos, often resulting in paradigm shifts that challenge long-held beliefs. One of the most groundbreaking examples of this is the discovery of exoplanets. Initially, astronomers believed that solar systems were rare and that our own system was a unique occurrence. However, the discovery that thousands of exoplanets exist, many of which reside in habitable zones, has profoundly altered our concept of planet formation and opened new possibilities regarding the potential for life beyond our planet. This revelation has expanded the horizon of what we know about the universe and our place within it. A similarly transformative moment in astronomy occurred in the late 20th century with the detection of cosmic acceleration. Observations revealed that distant supernovae appeared fainter than expected, indicating that the universe was not only expanding, but doing so at an accelerating rate. This discovery pointed to the presence of a mysterious force, now known as dark energy, and fundamentally altered our understanding of cosmic dynamics. Before this breakthrough, scientists had assumed that gravity would eventually slow the expansion of the universe. Instead, dark energy introduced a new layer of complexity to the field of cosmology, prompting extensive exploration into its nature. The discovery of the cosmic microwave background radiation further deepened our understanding of the universe. Initially predicted by theory, its eventual discovery provided crucial evidence for the Big Bang model. Tiny fluctuations observed in this radiation have become instrumental in revealing the universe's early conditions, including the distribution of matter and energy. These insights have allowed astronomers to refine their models of cosmic evolution, furthering our understanding of fundamental forces and particles that govern the cosmos. In more recent times, the identification of fast radio bursts, FRBs, from deep space has captured the imagination of astronomers. These brief, intense flashes of radio waves have defied initial explanations, leading to a host of new hypotheses about their origins. Some scientists speculate that FRBs may result from interactions involving neutron stars or even the possibility of advanced extraterrestrial technologies. Such mysterious findings constantly push the boundaries of our knowledge and illustrate the ever-evolving nature of astronomy as new information challenges established assumptions. Every new discovery serves as a stepping stone, revitalizing the pursuit to unlock the deepest mysteries of the universe. Amateur astronomers have also played a surprisingly pivotal role in advancing our understanding of the cosmos. Fueled by a passion for discovery and a sense of curiosity, these enthusiasts often make significant contributions to the field, contributions that professional astronomers may overlook. From identifying new celestial objects to making important observations that enhance existing knowledge of astronomical phenomena, amateur astronomers have proven indispensable. For instance, many amateurs have been instrumental in the discovery of supernovae. Armed with modest telescopes and cameras, they regularly scan the night sky, identifying these powerful stellar explosions. Their observations often lead to swift follow-up studies by professional astronomers, driving new insights into stellar evolution. Amateur astronomers are also crucial in monitoring transient events such as variable stars, comets, and asteroids. Regular observation of these phenomena is vital for understanding their behaviors and characteristics. Organizations dedicated to citizen science have recognized the importance of amateur contributions and now rely on them for consistent data collection, which leads to larger, more comprehensive data sets. These data sets are key to making significant discoveries that might otherwise go unnoticed. With the advent of advanced technology, more individuals than ever before are able to participate in the exploration of the cosmos. The rise of the internet and various online resources has created a space for amateurs to share their findings, tools, and techniques. This democratization of knowledge not only highlights the role of enthusiasts in astronomical discovery, but fosters a spirit of collaboration that enriches the scientific community as a whole. Through this collective effort, the pursuit of knowledge and exploration of the universe has become a truly shared endeavor. The cycles of observation in astronomy have long played a vital role in shaping our understanding of the natural world. For centuries, humans have turned their gaze to the skies to mark the passage of time. By observing the movements of celestial bodies such as the sun, moon, and stars, early civilizations developed systems for tracking seasonal changes, determining the best times for planting crops, and creating calendars. These cycles of observation were essential for agriculture, navigation, and the development of cultural rituals. Perhaps the most familiar of these cycles is the annual pattern of the changing seasons. The Earth's tilt and its orbit around the sun create seasonal variations that directly impact life on our planet. In the Northern Hemisphere, for example, the summer months occur when the North Pole is tilted toward the sun, resulting in longer days and warmer temperatures. Conversely, the winter months bring shorter days and colder weather when the North Pole tilts away from the sun. These seasonal changes have had profound effects on human societies, influencing everything from farming practices to urban planning. By tracking these celestial rhythms over time, humans have gained a deeper understanding of weather patterns and natural phenomena. The ability to predict weather trends has been invaluable, helping societies prepare for everything from crop harvesting to natural disasters. In essence, the observation of astronomical cycles continues to shape our understanding of both the cosmos and life on Earth, reminding us of the interconnectedness of all things. Lunar cycles, such as the phases of the moon, exert a profound influence on Earth's natural systems, and their effects ripple across ecosystems in ways that may not always be immediately obvious. One of the most striking examples of this influence is the way the moon's gravitational pull affects the tides. The Earth, the Moon, and the Sun align in specific ways during particular phases, leading to higher than usual high tides and lower than usual low tides. This phenomenon is known as spring tides. These extreme tidal shifts are critical for marine life. Many species rely on these changes for spawning, feeding, and migration, underscoring the deep interconnection between lunar cycles and life on Earth. In addition to these immediate effects, the moon's cycles also play a part in larger, longer-term astronomical patterns, which have profound implications for Earth's climate. These patterns, known as Milankovitch cycles, describe the way variations in Earth's orbit and axial tilt influence the planet's climate over tens of thousands of years. From the waxing and waning of glaciers to shifts in ocean currents, these cycles help explain major climate fluctuations over geological time. By studying these ancient cycles, scientists gain insights into past climate events and can better anticipate future changes, offering a more detailed understanding of the interplay between celestial mechanics and terrestrial phenomena. Throughout history, the evolution of our understanding of the universe has been shaped by the work of astronomers whose discoveries pushed the boundaries of science. One of the most compelling stories is that of Galileo Galilei, a revolutionary figure in the late 16th and early 17th centuries. With his enhanced telescope, Galileo made groundbreaking observations, such as discovering the moons of Jupiter and the phases of Venus. These findings challenged the geocentric model of the universe that had dominated for centuries. Galileo's support of the heliocentric theory, suggesting that the Earth and other planets revolve around the Sun, brought him into direct conflict with the Catholic Church. His views ultimately led to his house arrest, but he continued to work and write, eventually becoming one of the most influential scientists in history. Another fascinating story is that of Tycho Brahe, a Danish astronomer from the late 16th century who was known for his meticulous and detailed observations of the stars. His dedication to accuracy was legendary, but it was his dramatic and somewhat bizarre death that also captured the public's imagination. It is said that Brahe died from complications related to a burst bladder after refusing to leave a banquet to relieve himself. Despite this odd end, Brahe's data played a crucial role in Johannes Kepler's formulation of his laws of planetary motion, showing how individual efforts can have a lasting impact on the development of scientific knowledge. Then there's the remarkable, though often overlooked, story of Caroline Herschel, a pioneering astronomer of the 18th century. As the sister of the more famous William Herschel, Caroline initially assisted in his work after he discovered the planet Uranus. Caroline's own contributions, however, were groundbreaking in their own right. She discovered several comets and became the first woman to receive a salary as a scientist, paving the way for future generations of women in science. Despite the societal limitations of her time, she demonstrated that women could make lasting contributions to the field of astronomy. In the 20th century, Edwin Hubble made a discovery that revolutionized our understanding of the universe. Hubble's observations led to the realization that galaxies were moving away from us, providing key evidence that the universe was expanding. His work laid the foundation for the Big Bang theory and altered the course of cosmology. What makes Hubble's story even more remarkable is that he initially entered the field of science almost by chance. Before becoming an astronomer, he had a passion for photography, and it was his ability to combine his love for the cosmos with his unexpected path into science that ultimately led to some of the most significant discoveries of the 20th century. While these famous astronomers changed the course of history, everyday individuals continue to make meaningful contributions to the study of the cosmos. One of the most accessible ways for the public to engage in astronomy is through amateur observation. With a simple telescope or even binoculars, individuals can observe celestial bodies and report their findings to the scientific community. This grassroots involvement is a valuable resource for professional astronomers, helping identify rare or unusual events such as comets, novas, or even the discovery of exoplanets. The rise of citizen science has made it easier than ever for enthusiasts to contribute to scientific progress. Many institutions now collect data from telescopes and satellites, and volunteers can help analyze this data, detecting anomalies or classifying celestial objects. For example, projects like Galaxy Zoo allow participants to help categorize galaxies based on their shapes, a task that would be impossible without the collaborative effort of thousands of people around the world. Similarly, amateur astronomers can contribute valuable data on atmospheric conditions or cloud cover, aiding researchers studying celestial events and their visibility. Online forums and social media platforms have become hubs for amateur astronomers where they can share their observations, discuss their findings, and collaborate on research. These digital communities offer a space for people to exchange knowledge and inspire one another, amplifying the collective effort to uncover new phenomena in the universe. The growing network of engaged citizen scientists enhances our understanding of the cosmos and fosters a deeper appreciation for the wonders of the night sky. Throughout human history, mythology has played an essential role in interpreting the mysteries of the universe. Many of these stories reflect humanity's desire to understand cosmic events and connect them to our daily lives. A fascinating example of this is the mythology surrounding the supernova explosion that created the Crab Nebula, observed in the year 1054. Various cultures interpreted this event in their own ways. In ancient China, it was called a guest star, while in the West, it became the subject of intense fascination, leading to tales of celestial omens and signs. Similarly, in ancient Greek mythology, the Pleiades star cluster was believed to represent the 7 daughters of Atlas. The rising and setting of the Pleiades were seen as important markers for agricultural cycles, and their disappearance into the night sky echoed themes of seasonal change, loss, and longing. These myths, passed down through generations, illustrate how cosmic events have long resonated with human culture, often serving as metaphors for the cycles of life. The total solar eclipse, a rare and awe-inspiring event, has also given rise to countless myths across different civilizations. The ancient Romans saw it as a harbinger of disaster, while some Native American tribes viewed it as a fierce battle between the sun and the moon. Each interpretation reflects the profound impact that such an event has on the human psyche, as well as the desire to make sense of the unknown. These myths, though centuries old, continue to remind us of the ways in which humanity has tried to connect the mysteries of the cosmos with the everyday realities of life. In the modern age, while our scientific understanding of the universe continues to grow, the myths we create around cosmic events still hold a significant place in our cultural narratives. They remind us of our shared heritage, the depth of human imagination, and our eternal curiosity about the universe we inhabit. As we continue to explore the cosmos, both through science and through stories, we deepen our connection to the stars and our place within the vast expanse of the universe.